Good morning, everyone. We welcome all of the honorable dignitaries, learned delegates, respected professors, eminent scientists, research scholars, and students for this 3 days international workshop, summer school, and course preparation on solar splitting and artificial photosynthesis 2023. Now we entering into the first section of this technique this day. It will be my pleasure to invite Dr. S. Rajashabala on the stage as the session chair to introduce and lead the section. Our first speaker for the day, Professor Nicolas University of De Poitiers, France.
A very good morning to one and all present here. I am very much delighted to introduce the first speaker of today's technical session, Dr. Nicolas Alonso Vante. He is working as professor in the Department of Chemistry at the University of Poitiers. His fields of research interest are electrocatalysis, materials chemistry, and photocatalysis. He attained his Ph.D. in the year 1981 and Doctor of Science in the year 1984 from the University of Strasbourg. For more than 2 decades, he has developed nanomaterials based on transition metal and chalcogenides in metallic and semiconducting form. Moreover, he is the pioneering to utilize non-platinum and non-precious metal catalyst-centric chalcogenides to understand the complex process of oxygen reduction reaction in low-temperature fuels. To his credit, he is the recipient of Alexander von Humboldt Fellowship to do postdoctoral research during 1985 to 1986 at the Helmholtz Zentrum Berlin, where he further continued as a senior scientist in the Department of Solar Energy till 1997. He has received the awards of the National Polytechnic Institute, Mexico as a R&D Distinguished Graduate, the Mexican Council of Technology SNI 3 recognition as a Mexican researcher working outside Mexico, and in the year 2017 he received a medal from Russian Academy of Science to honor him as a to the memory of academician N.M. Emmanuel. He has 363 publications with citations of 11,407, H index of 57 and I-10 index of 173. One of his research articles has citation more than 700. From his citation, you could understand how his research works are more societal important. He has penned 2 e-books, namely Fundamentals of Electrocatalyst Materials and Interfacial Characterization, Energy Producing Devices and Environmental Protection. Then the chalcogenous materials for energy conversion, pathways to oxygen and hydrogen reactions. He holds 2 US, 2 German and 2 French patents. He is the potential reviewer for more than 28 journals, which include Nature Chemistry, Nature Reports, Langmuir, International Journal of Hydrogen and Fuel Cells, etc. Moreover, he served as member of the editorial board of Fuel Cells and the International Journal of Photoenergy. We are very much fortunate to have you as a resource person today, sir. Without any further delay, I hand over this session to Dr. Nicolas, and I request you to deliver your lecture on the hydrogen reaction, what factors affect the photoelectrochemical activity. Thank you, sir.
Yeah, thank you for the nice introduction. Good morning. Kalai Banakam, as you say in Tamil. First, before I forget, I would like just to express my thanks for the warm welcome in India, North and South. And I'm also grateful for the opportunity to collaborate in the Full Long Boat project. I know that any collaborative project can reach the exchange, knowledge, and also friendship. So that's why I'm happy to be here. Also, is one okay? Sorry for that. Okay. So let me start. The topic today is the hydrogen reaction, which factors affect the photoelectrochemical activity. When I was preparing this lecture, I didn't know actually what to do because it's so large, the subject. So I decided to make two parts, not so scientific and a little bit more scientific. Yesterday, we heard a lot about photochemistry, material science, and some words that you see here in that slide. The bit actually what here you have. For example, photocatalysis, efficiency, carbon, water, etc., etc. What I suggest today is what will be covered. So I have several points. I hope I will cover that in the time allocated for this lecture. I would like first to discuss the electrochemical versus photoelectrochemical system. And I will go here directly to show that here we have, here we talk together with the physicists because here we have the energy scale and the electrochemical scale. That's the most important thing to know, that the Fermi or the energy for the hydrogen electrodes corresponds to minus 4.5 electron volt. And you know that we can discuss with the physicists. And now I put here to the concept the reaction, the water splitting. Here the hydrogen evolution reaction, and here the oxygen evolution reaction. Thermodynamically speaking, the potential electron I place here for the hydrogen and here for the oxygen. And you notice that there is a difference here. That means that we have to pay for the energy to do this reaction. Even worse is the case for the oxygen evolution reaction. Now here I put a battery that I would like to charge. This battery that I would like to charge is the electrolyzer. Okay, so I have here an electrode working as a cathode and an electrode working as an anode. So the Fermi level of this material will be able, okay, to give electrons in order to evolve hydrogen, and here to deliver electrons in order that the hydrogen will evolve. And at the same time, you have the oxygen evolution reaction. Now, if we are, yeah, now here we have the photoelectrochemical system. What is important in a photoelectrochemical system is that the energy of the conduction band and the valence band straddle the energies corresponding to the hydrogen, for example, and the oxygen reaction. That is important. Otherwise, you will have only one reaction, the other reaction. The big problem is to develop the material able to fix this trouble between these two levels. Okay? So, here is a nice experiment published in the 70s by the Japanese group, but they used as material rutile. Here we work with anatase, okay? So this system more or less obeys what I said here. There is a straddle of this energy, but here is a photoelectrochemical system because here you create a special region in which you create an electrical field that will be able to separate the charges. So holes will be conveyed here, and the electron will be into the counter electrode to make the hydrogen evolution reaction, and here the oxygen evolution reaction. The church transfer here is so complex that means I don't know how many hours to explain here what happened at the interface. But believe me, this actually this photocurrent put in the same scale put here, this photocurrent actually corresponds to the oxygen evolution reaction. We couple that with the density differential spectrometry, and indeed, this belongs to the evolution of the oxygen reaction. Now, what I want that you compare, young guys, is that this process carried out on the metallic electrode catalyst is shifted here. And that's really, that is the stored energy released by the impact of photons into the semiconductor electrode. And that is the beauty of photoelectrochemistry. But the problem is, of course, in order to generate this photocurrent, you need to have a good material able to absorb energy. And we want that the energy be in the visible region, not in the UV region. That is in the UV region, in the ultraviolet. So there is big problem. Now come back to the dark process. That is the best catalyst, so-called benchmark material that's based on platinum electrode. And here you see the difference. Look, we compare this in two media, acid and alkaline. And what you have here, this difference, that means that this electrode, even being the best catalyst, is bad in the alkaline medium. Okay? Similar effect we observe when we do the oxygen reduction reaction. So the halfway potential here shifted to the left instead of going in that direction. That also means that the chemistry, the complex chemistry at the surface is rather different. And that's one thing that we have to think of. We worked some time ago with this problem. And see, there is a very interesting system, so-called the micro fuel cell, where we use as platform in order to test many materials in a very short time, avoiding the use of a membrane electrolyte. And the beauty here is that you can measure the anode and the cathode of fuel cell at the same time, so you see which electrode is still varying with the applied electric potential. Okay, so we see here that the improvement of the cathode is really very important, because we have here the power density is increased by 60% just by modifying in an intelligent way the catalytic size of platinum. In that case, was done here using a small amount of molybdenum and making a small alloy with copper. As you see, the system becomes more and more complex. You want to have a better system to make reactions. Okay, photocatalysis versus photoelectrochemical cell. That is the principle of photocatalysis, and that's the principle of photoelectrochemical cell. Here we decide that the electron will be only one vector, only putting electrons to make reduction process or to make an oxidation process, which is important to keep in mind for those people that are working with material, semiconductor material, is that it's important to have this separation, the quasi-Fermi level of electrons, right, and the quasi-Fermi level of protons. That is the driving force of the system. You don't have that, forget it. You don't have not a good system. So that is the driving system here, driving force, and also the driving force here in order to perform on the elimination the photoreduction, hydrogen evolution reaction, or oxygen evolution reaction. So artificial photosynthesis actually needs to have, in order to mimic what the plants do in the natural photosynthesis, that we have a system able to generate electrons and holes, that we have band gap, adapt the band gap and the position of the Fermi of the energy level of the balance and conduction band, and of course to have spectral region. The other point is to have the separation and transport of these photogenerated hole and electron pairs. That's why we have to also to study in the material science, carrier diffusion length, crystallinity, carrier mobility, etc., etc. And at the end, of course, what we want to have is an efficient interfacial charge transfer. Okay, this transfer could depend also if you have a presence of surface states of resistance to do this reaction available. Now, with this knowledge we have here, the energy for the hydrogen electron and the energy for the hydrogen, for the oxygen electron. In between, I wrote here, because that is also important to fix CO2. That is also a big challenge in electrochemical world, how to produce the best catalyst to do this. And you can observe that all these process, multi-electron charge transfer process, from 2 to 18 electrons, in order to produce fuel, all this is around the potential of the hydrogen electron. So if I am able to develop a system, I could fix the problem of greenhouse gas, right, by fixing CO2 and evolving oxygen. Or in this easiest way is to evolve hydrogen and oxygen, in the case of the water splitting. All right. So that is again the conversion of the electrochemical versus the physical scale in energy. Now let's put all together now. Remember the song, Beatles. I hope you will understand. Okay, I hope so. I saw very quickly that the oxygen revolution reaction takes place here, a very high UV potential, okay? And when you use a semiconductor, okay, then you can observe that the oxygen revolution reaction takes place here. So now what we need is to have a material able to evolve hydrogen. Let's say this is this process here, okay? And then what is important to take care now is that we want to develop a system able to increase the operational current here, okay? And one way to increase this operational current, that means that the system will put it together, could work alone, not to fix a potential. That is the idea. Okay, now, I think one idea is not to oxidize water, but to oxidize glycol. This is an alcohol, because in the oxidizing glycol, you can also obtain high value added products also at the same time. And then you can see that with the same curve here, you have a higher solar to energy conversion process. So that is the dream, okay? Still a dream. All right, I want to talk about CO2 reduction. And I will talk about other biology principles here, because that is what's important to work in biology. At the same time. It's okay? No? All right. I would like just to show a very recent example that was not developed, unfortunately, not in my group, but some other group, Korean group, for example. And that's interesting, the principle. Look here. They use highly doped silicon, like a metal in that case, and they deposited this species here, and they evolve oxygen. Look at the potential. The thermodynamic potential is 1.23, and that goes around 1.6 volts. Similar to the best material, like catalytic material like the iridium oxide. All right, now, using now silicon N-type, putting the same species, then you observe now that this process is being carried under illumination. So this is not a big shift, but anyway, an interesting shift, because you see that the potential that which takes place in the dark is shifted to almost to 1 volt. So we have here a part of the solution of the system. Important thing is that it's not only silicon. It's very important also to engineer the surface of the material. This is very important. The interfacial engineering of semiconductor material needs a way how to produce this kind of layer in which the whole could be easily conveyed, of course. All right. Said that, I would like to go into the materials pragmatic path. Well, probably you are aware that 90 natural elements that make up everything in our world, okay, there's not much. So for those guys who like to use the smartphone, you can see how many elements are involved in this technology. In electrochemistry, we talk about precious metal and non-precious metal. So everything that is not platinum is non-precious metal. But even in that case, we observed that there are limited amounts, for example, nickel, copper, molybdenum, etc. So that means that we have to pay attention in that, because with the development of the hydrogen economy, as is reported here, by different agencies like the Hydrogen Tech World, International Energy Agency, the International Renewable Energy Agency, the Bloomberg New Energy Finance. They say that there will be multiplied in several factors the utilization of these materials. So you see here that, for example, for the electrolysis, which we use iridium, that will increase up to 90%. And all, even if they are not precious, they will also increase. So we have to pay attention to that. That's one thing. And that is the different technologies that are now used, for example, say in proton exchange membrane fuel cell. All right. Here is the carbon capture and storage, and also the polymer electrolyte membrane electrolyzer, etc. So if we develop in a very, let's say, not planned way, we will risk to use a lot of materials in not a very intelligent way. And that is important to take into consideration. Now, the question is that hydrogen good? That is the question now. Okay. So, everybody knows that I just put together here that 1/6 of the energy per liter corresponds to the hydrogen in relation to the gasoline. It's not much. Moreover, it's 2 times the energy per mass. What does it mean? That we have to use high pressure. And that makes the vehicle a little bit heavier. In 2021, the cars that use hydrogen, just the ratio is equivalent to 1 car over 4,000 cars. So there is still a small market. And the Green Hydrogen International has reported that there will be a hydrogen city in Texas with 60 gigawatts solar electricity, correspond to 2.5 10 to the 9 kilograms per hydrogen per year. That sounds very nice. But where do we get it? We have water, okay, we have methane, and here's where the problem starts, okay? And that's why the scientists invented color for hydrogen. Hydrogen has no color. And the color is actually due to the, the mode of production of this hydrogen. Okay, so, well, we have the black and the brown color, and then we have the gray color. We use this reforming process here, consuming natural gas and methane in order to produce hydrogen. But the problem is that production of CO2 corresponds to 8 tons per ton of gray hydrogen. There's another color like the blue one and turquoise. And why not the pink? Because people think that the nuclear energy is also an alternative. I don't know if you will leave that, but anyway, that is also comes into the play. And see, there are many guys here involved, like the oil and gas industry. They pretend to say, this is really good for the environment. Is that true? Okay, let's see what the colleagues say. But you know that only 4% of the green, that means for water electrolysis to obtain hydrogen, is really ridiculous compared to the hydrogen produced by other medium. That means that we have a lot of possibilities to develop such a technology. So here we have how green is blue. So I invite you to look at this paper, okay? Because they consider and they make the balance of all the reactions that could be involved in this process. And they arrive at the conclusion that the blue is not so blue and the gray is almost blue. Because that is the production of grams of CO2 per kilowatt hour, which is not very far from 486 grams per kilowatt CO2 corresponding to the blue one. But you see that there is increased the green energy. Anyway, green energy is not really green energy, 100%. Okay, so that there is another paper that says how green is the blue hydrogen. Okay, all right, they make this balance. So it's a paper of 19 pages. So I invite you to read if you want. Here the main message is that greenhouse gases from green hydrogen products produced with solar energy are ideally 1/4 from gray hydrogen. The other problem is the price. I don't know. I just checked this morning what's the price of hydrogen produced by solar. And you see that it's very expensive. Here go between 5 to 23. Probably it decreased a little bit, but I think this morning for the Indian producers of green hydrogen is around $3 to $7 per kilogram. There's also the problem of water. Do we have enough water in the world? Yes, 98%. But not all water is important for that. Okay, because we have to extract it all. Fresh water is not much. And here there is another paper that makes such a balance. Does the green hydrogen economy have a water problem? Yes, there is problem. You see here that the agriculture is the most water that is used and thrown away, and the water that comes back again. That was the data of 2014. And that is in a logarithmic scale, okay? It's not linear. So you can see that the future hydrogen economy will need such an amount of water, and water that will be actually withdrawn, but even less than the water used for fossil fuels. But the future is not so black, because if we develop this technology, this should be obsolete in the future. That's why the balance could be at the end positive. All right, that is my, let's say, general information about the problem of hydrogen. Now I would like to go a little bit more scientific. So I would like to discuss point 4 electrochemistry, electrocatalysis basics, in order to explain the different data that we have obtained in the laboratory. So actually, what is electrocatalysis? Well, electrolysis is to have an electrochemical interface able to do complex electrochemistry at the surface in order to produce a fuel, for example, or environmental friendly energy. That's also important to take into account that there are surface structure and composition. The surface plays an important role in electrocatalysis. And as you all know, fuel cell reactions actually is based on platinum. That is the preferred material, at least for the acid electrolyte. So, so let's say the problem of hydrogen is that, we have the different energies here, the proton plus electrons, and at the end we have the product. But we should not forget that if we have one electron, we have a minimum one intermediate step. You have two electrons, two intermediate steps, and so the difficulty is increased. So now the situation is to try to develop material able to make this intermediate energy, all right, and try to fix this intermediate energy at the same level of the hydrogen and the oxygen. In that case, we can say that the thermodynamic overpotential is zero. That is the goal, okay? And this goal is obtained, and that was set a long time ago by Paul Sabatier, and that's why the name, well, not for electrochemistry actually, it was for catalysis, this idea. And that's why we have to have an optimal interaction. The optimal interaction is not too strong, not too weak. So that here we have two legs, okay, too strong, too weak, and the optimal should be here at the maximum of this volcano curve. Okay, so I will come back with this. What is the most important reaction? The Fulmer, Perovskite, and this. We have, of course, Tafel mechanism. So I come back again with this. The mechanism of the hydrogen pollution reaction would be represented by the Fulmer-Tafel mechanism, the so-called Langmuir-Hinshelwood system, or the Fulmer-Perovskite Li radial mechanism. So these two processes play an important role in the hydrogen revolution reaction. And that was calculated and measured and taken as a descriptor. Actually, the energy of absorption of the intermediate species here. That's why it's called the descriptor of the system. And you see that the best guy or the bad guys, I don't know, stay here, platinum. Molybdenum, that's if I try to go there, but I don't think that will reach that point. Sorry for you guys. We will stay this here. Okay? So what we can do is to improve platinum. We're going to have to use 100%, but some percent of platinum. I think that is the future, what I see at least, in my opinion. Sorry, I am wrong or I'm right, I don't know. Okay. Here's some electrochemistry principle. For those who done electrochemistry, we have two reactions, okay? We have two reactions, the oxidation reaction, the reduction reaction. When I added this, we have this back curve. Important thing is this difference here, because to measure the electrocatalytic power of the material, that power is measured through the exchange current density. This is important, and I will talk later about this, okay? Keep in mind that. Okay, so that is the so-called Butler-Forman equation. Is the most simple one for the moment, okay? So we have the anodic and cathodic term, and for that we can linearize some part of this equation to obtain the so-called Tafel equation. That's what the current electrochemistry students do every day during the electrochemistry of material. All right. Then we transform this exponential equation into a Tafel equation, which is semi-logarithmic form. I recall that Tafel was not an electrochemist, he was an organic chemist and trying to develop synthesis. They use mercury in order to make the reduction process, and they found phenomenologically this equation. This equation found his concept by the work of Butler-Forman 30 years later after the publication of Tafel equation. And that is this one, all right? So you see that the intercept here, that is the measure, that is the point that corresponds to the exchange current density for a reaction. So we have several figures of merit. Here is the exchange current density, the Tafel slope, etc. And the ways to report the current density here are given by the geometric surface. That is the most common thing, but it's not really true. You take into account the real surface, then you have to report the current versus the real surface. But that is not true for electrocatalysis. Then you have to try to think about what are the active sites, and then you go to the EXA, electrochemical active surface area. The most important one to talk with the catalyst guys and electrochemical guys is to transform this in tough turnover frequency number. Only in that case we can speak the same language. Tamil, for example. All right. So, so now here are the experiments. Indeed, look here. We have platinum, iridium, and palladium for the hydrogen oxidation and reduction reaction, oxidation and reduction process. You change this, the acid in the alkaline, there is almost 2 orders of magnitude less than the acid. Why so? I'm not asking an answer, all right? You will see the answer later. Now, when you put this in a linear way, indeed, you have here the curve corresponding to platinum, iridium, and palladium. The shapes are very different for the oxidation reaction, and also a little bit different for the reduction of proton. Now, when you change from the acid to the alkaline, the shape again changes. And that is important because the system is telling, oh, here, the species acting on the surface, we are not the same guy, all right? We are white or we are black, I don't know. So that is the surface chemistry play on the material. So that at the end, the conclusion is that the exchange current density here is actually for each system 2 orders of magnitude different. Now the question is, there is a chance to improve this? Yes, of course. I give you the answer. How? You have to do the experiment. That's why I would like to discuss now the role of the a strong metal support interaction. That is very important. Everybody uses support. Don't forget that support may also interact in a positive way, mostly than a negative way. The situation is how to do this, that this system works, okay? So I will enlighten this with this example, with the hydrogen reaction. So here you see how this is the bar errors that you find in the literature, how the activity or the exchange current density may vary according to the nature of the element and also according to the nature of this support effect. Some time ago, we published this because we were able to have here sp2 carbon. On this sp2 carbon, we photodeposited platinum, and with the calculation and the measurement, we observed that there is a strong bonding, a hybridization, okay, of the orbitals with sp2 orbital of the support. And that really gives an interesting interaction of the catalytic side. And therefore, we study this from the solid Vulcan carbon nanotube treated differently chemically in order to change the order of sp2 at the surface of this material. And with the help of Raman, we can actually determine the length of the crystallinity correspond to sp2 and try to see if there is a difference in their catalytic activity. Okay, I will do the story very short. Here you have the XPS measurement. Here is the benchmark material. Here is the material, the photodeposit on carbon. And here are the different support carbon nanotube with different sp2 content. And what you observe is it's this important shift toward lower binding energy. It's not that platinum becomes -1. That not exists, okay? So that means the electronic effect of platinum is not the same depending on the support that you used. Indeed, when you measure the oxidation of hydrogen and reduction to proton, you see how it is affected, this reaction. So now, actually you observe that, and that goes very well corresponding to the length of the crystalline plane of sp2. I decrease here, and you observe here also in the top of plot, the same curve. And when I take this small part here, which is called the micro region, because it's, look here, 10 millivolts plus minus. This part is linear. That recalls you that we are working with Ohm's law, okay? So that the straight line gives you the resistance. Here, that delivers the conductance because it's I over B or 1 over C. So if the slope is bigger, that means that the resistance is lower. The transfer resistance decreases because of the fact of being modified the electronic property of the material. That is what we call the electronic effect. But is there more? Yes, there's more. Because now what we did is taking into account this support, we did the self-stripping. I don't know if you know what self-stripping. You polarize the material, you absorb CO, and this CO absorbs in a monolayer. Then you scan to deposit the potential, and you will observe that the CO absorbed will be oxidized to CO2. CO is a very interesting molecular probe because that really probes the electronic property of the material. That is a very interesting tool. It's not very expensive at all. So, and that's indeed what you observe here. Look, it appears here this kind of wave. That means a CO absorber on platinum is being affected by the surrounding medium, which is sp2 region, which acts as a OH source, okay? And that helps the oxidation of CO2. And besides, that's what I call the chemical effect, but the electronic effect is there. Yes, you see that the main peak is also shifted towards negative potential. So to make things a little bit short, we can calculate the charge here in two mediums, either in acid or in alkaline. You see the alkaline, we have an increase of the charge, all right? And that goes almost in parallel with the exchange current density of the system. So that we can say that how this effect could be illustrated when you do the hydrogen under potential deposition. There is this shift. The bond between platinum and hydrogen changes because there is a shift there. With the oxide, I want to discuss this in the other way. It's not so favorable with the oxide. All right. So we have this strength of a bond between platinum and hydrogen. So that we have chemical effect, electronic effect. That is the take-home message, okay? Is that a serendipity? No, that's true. And, okay, that was a support effect based on carbon. That is a known precious metal. You agree with me? Known precious metal. We have a lot of carbon. The problem is how to construct sp2 large domain for that. And then here there was a paper from my colleague Rado, I forgot his name, but it come later, which they put a metal inside another metal. Okay, that is like a core shell structure, and they tested that. We know that with the classical model we have an optical binding. That means that have the metal with the hydrogen absorbed. We can also have the functional model as I shown with the sp2 domains. But if there is an electronic effect, this bond energy should change. All right. And this appears to occur in this system. So in order to convince that, I hope that you understand this cyclophotometer curve. That is an alkaline, that is here, the hydrogen region, and here is the oxide region. Important thing is this peak. This peak actually reveals the presence of OH. And that is the problem of platinum in alkaline, the OH, okay? So, in modifying that, look at here, they put a ruthenium, a platinum, palladium, a platinum, gold, and platinum, and they behave differently, and you observe that it's also affected here, as well as here. So the result was that the charge in acid goes in that direction, and in the alkaline, we observe how the amount of OH absorbed decreases when we have different core, ruthenium versus palladium versus platinum versus gold. All right? So, and that shows that there is an electronic effect here induced by the presence of ruthenium atoms inside in the core of the particle, and that modifies the electronic effect, and that increases the exchange current density of the reaction. All right. So this effect was interesting to learn about that. And that's why I would like to show you now one paper I published this year. If you want to read, okay, if not, that's okay. This, in which I summarize 20 years of experience working on nanoalloys. Look here, I put all together. Okay, when you have a lot of data, then it's important to rationalize what you learned some years ago, and you see you have the same point of view at present. That's what I did. So I put here actually different alloys. Here correspond to the alloy 1, 1, 2, 2, 1, 3, 2, 1, etc. And with the material synthesized and measured through hydrogen, we can titrate how much platinum the surface is. And you observe that not all alloys here obey this position. What does it mean? Does it mean that the atoms by the surface, they are not really glad? They have to find an equilibrium, energetic equilibrium, which is induced by the surface energy of the material. That is the reason. Now the question was if nickel, chromium, cobalt, and all this stuff affect the hydrogen reduction reaction in the same way as carbon, okay? And the answer is yes. I give you the answer. And now, which is very funny and interesting, when you have ruthenium or platinum, not core shell, alloy at the surface. Look what happened here when I have acid medium and alkaline medium. Actually, we observe the same curve, the green curve here. Does not change. Okay, for the alloy. But if you measure platinum alone, you have here, this is the answer for platinum, and there's the answer for platinum. So platinum actually, in this domain, says that there is OH adsorbed that favor the oxidation of CO at rather low potential. That is the learning, that is what that result teaches us, okay? So, oxophilicity exists for this material in acid or alkaline. That's a good thing because you can use this cathode or anode for hydrogen in both medium without being affected by the chemistry of the surface. That is the, okay, you know that is the different reaction, what thing takes place at this material. Now here I summarize all these guys here. That is in acid and that is in alkaline. And look the difference that happens when you change the electrolyte. So you here see the effect of the partner. Here's nickel, chromium, cobalt, etc. And that is, if you do the experiment of hydrogen in acid and alkaline, you will see that this part actually favors the catalytic activity of platinum. Because the catalytic activity, the site is actually platinum, not nickel, if not chrome, etc. So here, we estimated the strengths between the hydrogen and the different catalysts. One is negative, one is positive, and this is observed here in the microdomain of, you see that the platinum ruthenium that I showed before is a little bit more important than the other one. But now when I compare with the non-precious metal, that means the carbon sp2 domain, this guy here below. And that is an interesting view because I can modify platinum without using very expensive partner like sp2 carbon. Okay, I think that is almost my last slide. I summarize here with this picture again, saying that the hydrogen reaction in alkaline kinetics still keeps many unknowns. So that means that you have a lot of work, you guys, to try to understand that and improve. The rationale for high hydrogen oxidation reaction over potential lays in the fundamental change of the reaction mechanism, and not simply due to an increase in the hydrogen binding energy. There are more. I don't know. So it's important is materials engineering must come into play. Okay? So, all right, that was my kind of conclusion. I summarized some papers that we published in the last years. There are some, these books also contain some of the concepts I presented today. And with that, thank you very much.
Thank you for your wonderful lecture on the hydrogen reactions. What factors affect the photoelectrochemical activity? Now the session is open for audience.
You understood everything or nothing?
Thank you for the lecture. I think we can never have enough of fundamental electrochemistry and advanced electrochemistry, and I think that was really nice. I'm thinking that maybe one of the reasons we both in the high temperature electrochemistry and let's say normal electrochemistry, one of the reasons we struggle is that it is very complex field and it is very interdisciplinary, and we have a tendency to work in certain boxes. Let's say one is good in electrochemistry, but then you have the materials aspect and then there are other as physics versus chemistry and things. And but just to take one specific thing, and a question to you is then, in my lab, the high temperature electrochemists, they use impedance spectroscopy. The photoelectrochemistry people, they don't use impedance spectroscopy. So I would ask you, is there any use of impedance spectroscopy in the field you described that is not sufficiently exploited? That is the question.
Okay. Of course, we use impedance electrochemistry. I didn't show anything about that. I worked many years with impedance spectroscopy, but I didn't publish. I did not publish a lot on that, but not even a lot. Several papers, because at that time we think that you can simulate an elephant. Mathematically, yes. Physically, that is the question, right? So one way I understood complex impedance electrochemistry was to vary temperature. And going from the room temperature to the nitrogen temperature, because I work cryo-electrochemistry. And there is a huge difference in temperature. And that we see which element in the impedance spectroscopy change with temperature. And that was interesting because we could, of course, determine the activation energy, and also discover that actually the process, for example, oxygen evolution reaction, is controlled by the entropic factors, not by the enthalpy factors. Yes, we do that. Electrochemistry in dark, also in light. But in light, you know, I don't suggest the student to do complex impedance chemistry with powder. It's so complex. Either you have a good electrode, planar electrode, and then go petit à petit, I would say in French, little by little, to understand the complexity of the system. Yeah, I agree.
Thank you.
Yeah, so no doubt it's a very, very brilliant talk. And thank you so much for giving us so nice overview of the entire mechanism of hydrogen generation and water splitting specifically. So you have not mentioned anything about the iridium oxide. So you talk about iridium, I saw several times. But isn't that be comparable with, because I saw iridium oxide is maybe much better for oxygen evolution, right?
Yes, in acid medium.
Okay.
In acid medium, where other elements based on non-precious metal can compete with iridium oxide and alkaline medium.
I see. And the question number 2 is, all these supported things like carbon, they all are carbon, like carbon nanotube and then Vulcan 72 and all these carbon, these all are supported carbon you are comparing?
The commercial material are all supported on amorphous carbon.
I see. Okay. And this platinum ruthenium, platinum iridium, platinum nickel, all are in core cell form or alloy form or side by side?
I didn't show. I invite you to read my paper. We have, of course, X-ray diffraction. You calculated the alloy. Yes.
So they all are alloy, right?
Yes. Yes.
Okay. So no the supported catalyst like
It's supported,
nickel atom?
supported, but the support is the same. So
Okay.
that allows us to understand the interaction between one metal with the other metal.
Because the comparison are really interesting. But thing is that if platinum ruthenium, if it is in alloy form, is more active, or in a single atom platinum and single atom ruthenium side by side sitting in more active.
Okay.
So that
Look, what I show here is two different things. I'm sorry for that. You realize. One, when the ruthenium is in the core and platinum is in the shell. That influences the reaction for hydrogen. Now, if you put platinum and ruthenium separate and together like this, then you see the Langmuir-Hinshelwood effect clearly, okay? And that's what I show, that in alkaline as well in acid is behavior is rather similar. So the oxyphilicity is done by ruthenium. I didn't mention a lot, but tins also do this work only in acid, but not in alkaline. But tin has another property that I did not mention. Tin with platinum makes platinum more resistant to CO contamination. Okay?
Anyway, thank you so much.
Hello, sir. I have a question from the slide all together now, where you showed the comparison of different material based HER and OER. I just wanted to ask you whether the curves that you showed in your graph, was it was it just the drawing, or was it really to differentiate between HER and OER? Because we all know that the type of curve that is drawn in a graph, it tells a lot about the kinetics of the reactions involved. So I wanted to know that the two kinds of curves that you showed in the graph, was it just to differentiate the graphs, or does it actually have something to do with the kinetics involved during those reactions?
Yes, it is schematic, but that shows reality too. The trend, you should keep in mind the trend.
The trend.
Like that.
Okay, thank you.
Yes, of course. I don't know about most.
It's not about mobs. Thank you. Very nice talk. Wonderful to listen. Tips to engineer the interface. You mentioned interface because I think the interface engineering is so crucial here and everywhere where we want to do the transport phenomena, whether it is electron or other mass transfers. So what are the tips for everybody sitting here and want to develop a new material?
To increase the energy, let's say balance, the conduction band and valence band, you have one way, either you use one semiconductor, which is visible, or EV only. If you want to have this energy and you want to use visible, then you have to use two semiconductors. But the difference of energy should be in that way, so that their sum accomplishes this high energy. That is one way, all right? That is the tandem cell, so called. Now, what it shows with silicon, which is interesting, how to engineer the interface. The problem, for example, we worked with a problem in Pache about the photocatalytic process with the unknown TiO2, is how to make the spectral region higher. One way is, as I discussed, is to try to modify the interface at the surface of the material with another guy, like perovskite, with a certain ferroelectricity in order to increase the band bending of the system. That is one of, that is engineering the interface. Yeah.
Thank you. Student side. Ask any basic questions. No problem.
Sir, it's a nice talk, sir. Sir. Sir, actually, I want one clarification for electrochemical cell. So we are working with electrochemical cell is a 3 electrode system. Sir, that. Okay. So that working electrode is a surface area is important for HER and OER reaction. So that. Sir, is audible? No. Sir, that working electrode is there, it's electrochemical cell.
Yes.
Yes, sir. That working electrode surface is important for HER and OER. Is that is important or not? That one clarification.
For any catalytic process, the surface area is important.
But actually, it's a small area of the. Sir, we are using some other substrate, such classic carbon electrode or some other FTO or ITO. So, what is the difference between for HER and OER process?
Well, you can differentiate in the sense that what makes it work. catalytic effect.
Uh-huh.
And that is the real surface area that you should take into account.
So, it's okay.
Okay? The site density. Oh. Hello, you have
Hello, sir.
Yes.
Thanks for your nice presentation. So I have to ask one question, sir. So at the time of acidic medium as well as basic medium, that can affect your material. So what will happen when we can use sodium bicarbonate or carbonate material, carbonate compound, so that whether that one is interact with your material?
You're talking about alkaline medium?
Yeah. So you mentioned that hydroxyl that can interact with your material. If suppose we are going to use carbonate, sodium carbonate or bicarbonate, whether that can interact with your material or not?
I don't know. Sorry.
Okay.
We can discuss later. I don't get your question. Okay?
Okay.
Thank you.
Sir, I have one question. You mentioned hydrogen can be a green hydrogen, blue hydrogen, gray hydrogen. Which type of hydrogen can be generated more?
No, slowly.
Okay.
I-
Hydrogen can be labeled as green hydrogen, blue hydrogen, gray hydrogen. Which type of hydrogen can be generated more? Whether green hydrogen, blue hydrogen, or gray?
As I said, the green hydrogen is up to now 4%. Most of the hydrogen is gray, blue, turquoise, and that stuff. Or fossil fuel.
Okay, thank you, sir. So thank you for your wonderful lecture.
Thank you so much, sir, for giving your valuable insights on the topic of photoelectrochemical. And also, I thank Dr. S. Rajesh Abel on the behalf of SWAB organization team for serving us the session chair. Now, I invite Dr. S. Rajesh Abela to honor Professor Nicholas with the momentum. Thank you so much, ma'am. Now, I would like to invite Dr. A. Siva, Assistant Professor of School of Chemistry, to honor Dr. S. Rajesh Abela with the momentum. Thank you so much, sir. Okay, then now we enter into the second plenary session. I will be privileged for me to invite session chair Dr. A. Siva, Assistant Professor of School of Chemistry, Madurai Kamaraj University, introduce and lead the session, addressing the speaker Dr. K. Smuggle, Institute for Energy Technology, Norway, to an esteemed audience.
So, good morning to all. So, it's my honor to welcome you on behalf of the 3-day international workshop and summer school and course preparation on solar water splitting and artificial photosynthesis, SWAP 2023. So, organizing committee of School of Chemistry and School of Physics, Madurai Kamaraj University, Madurai. It is a great pleasure for me to introduce our honorable speaker today, Dr. K. Sumagal, who is going to talk us about the functionalities and properties of applications of yttrium oxyhydride mixed anion films. So Dr. K. Sumagal, working as a senior researcher in the Department of Solar Energy, Institute for Energy Technology, Norway, from 2007 to present. So in addition to that, so he has various professional experience such as ERA chair, so leading researchers Institute of Solid State Physics, Riga, Latvia from 2023 to present, and also editorial board member in materials letter, and senior researchers in Institute of Physics and Technology, Uzbekistan from 1993 to 1995. His research interest in various fields, so such as chromogenic materials and devices, solar cell materials, and solar cell fabrications, photocatalytic process, artificial photosynthesis, theoretical modeling, and defects of impurities. In addition to that, his research in activities, so he has published more than 150 publications in well-reputed international journals, and he has published 3 book chapters and 8 international patents. His Hutch index, it's around 32. He has completed 6 PhD and 6 ongoing students, and he has received various awards from various resources, so such as Prize of Latvian Academy of Science on most significant scientific achievements in Latvia, so in the year of 2022, and premium of the Third World Academy of Science twice on 2003, and medal and prize of Russia Academy of Science December, Moscow in Russia on 2001, and Cobas Fellowships USA received on 2000, and that he received a lot of fellowships in going on in lengthy way. In this short introduction about Dr. K. Sumagal, I invite plenary lecturer. I request today's session Dr. K. Sumagal to deliver his presentation. Thank you, sir.
Hello, everybody. Before I go, I start my lecture. I would like to say you that now in the school, about 60 people are participating physically. And yesterday, in the online regime, about 245 people were watching it online, which is very good indicator. So I'm very happy to say that. Now let me start the lecture. So the lecture title, Dr. Siva already mentioned it. It is related to smart windows. I called it about smart windows. It's because this is to today the only functionality that is coming close to the market. This is new material, and since it's new, we study all possible properties and searching for functionalities to commercialize it. So we found this material, discovered it, and commonly in academic institutions, they will study properties, publish article within public funding, satisfy curiosity, and that's all. But we are going in different road. We want to return it to public in terms of scientific product. It can be either breakthrough result, or it can be either finding some key materials properties that can be in the future commercialized. So the smart window functionality to today is the only one which is coming close to commercialization. We reach it to today technical readiness level of 7, and we started we started from materials discovery, study of properties. In 2017 we started a spin-off company. And about 1 month ago, the company printed this photochromic film by roll-to-roll deposition unit on a 250-meter long polymer substrates with about half meter width. So this is a very good indicator. But many other functionalities of the material is unknown. So this is the company that we called Sunfade, Dynamic Photochromic Solar Control. Initially, it was IFE-owned company. IFE, it's Institute for Energy Technology. Huh? Okay. Yes. Yeah, and to bring it to this level of TRL, technical readiness level 7, we had the following projects. Technical readiness level, it's mostly used in European Union. It is indicator, it's parameter that shows where we are as compared to basic science, fundamental basic science, and market. So then there are 9 TRLs in general. So the ninth one, it's the last one. If one successfully passes 9, then it will go to commercialization. So today we are on TRL 7, moving to 8 and 9. So demonstration is ongoing on a demonstration house. In particular, I brought two boxes of these smart windows. One will be tested in outdoor conditions in Madurai climate conditions. The other one will be tested in Kerala climate conditions. The climates here different. In India, in Madurai, its humidity is very low and hot. In Kerala, humidity is high and hot. In Norway, around Ife, we already did this testing in outdoor conditions. It's working. But we cannot bring it to the market without this type of systematic testing. Even within Norway, it's not yet systematically tested. I will say later on in subsequent slides. So, if we analyze history of Windows, Windows came out to the scene in 13th centuries only. Before 13th century, the light to get into building, people just made hole on the wall. But then in the winter time, one should protect to keep heat inside. Then they were closing the hole with some a tray or something like this, or some cloth. But then windows came to the scene. But then windows in all the times were made very, very small. Like this is a window of one of the buildings in Trondheim in Norway. And this is a picture that I made when I visited University of Poitiers, France this year. As you see, two small windows. It's because if they make windows those days, then heat will just go out. Of course, light will come in, but it's on the cost of heat getting out. The point is, if window size will be made large, then there is no heat control only. So then, but living standards of people are increasing from year to year. In today's day, people would like, for example, to see outside being inside building. But if that's if to satisfy this demand, then we should be able to control heat transfer from the window and change of color according to market demand. I mean, many of you are working, I think, in the field of photovoltaic technology. You might hear about the word colored PV. Because the highest efficiency is provided when color looks like black or blue. But now market wants to do it like red color, green color as well. Color should become, it can be less efficiency, but this is the requirement of the market, and we should give to the market the product that they need. And so from this point of view, the same requirement applies to windows as well. And all outermost walls, there is some intention to make from glass, but then we have to control its color and light reflection as well. It's not always useful. For example, can you imagine if this smart energy saving window is just in front of parking place, car parking place, then the huge heat waves would be reflected. And if it falls to a car, then a car just will be melted. So it's, and the same applies to if the light will be reflected and falls on another neighbor's building, if there are some plastics that will be just melted. So one should really, and then also another interesting case is one can control heat reflection that can present interest, for example, for space satellites as well, to make them invisible to night vision devices. So a lot of possibilities. All of them can be solved within the topic called smart windows. So these are examples of today's some of the buildings with outermost wall made of glass. And even the first class cabins of some flights are made also from smart windows. Yes, and all these smart window can be formulated, classified into one topic called chromogenics, or chromogenic materials and devices. There are several branches of it called electrochromism, thermochromism, photochromism, magnetochromism, piezochromism, gasochromism. Electrochromism, it is electrochromic windows, are type of windows with controllable optical properties that human can control depending on what they wish, which color they wish. For example, in the long flights, for example, in Turkish Airlines or in Emirates Airlines flying to Japan, they have this type of system. Press one button, that there is no need to close the window. It will be make just invisible, dark. And close another button, it will be bleaching. So this is what stands for electrochromism. Earlier, these electrochromic windows were not in the market because they were very expensive. It was around 1,000 US dollars per square meter. But since discovery of polymers, community is constantly working on improving each and every material's property, optimizing them. One of them is electrolyte layer, and they found, the company's certain material that can, operate within very long time, and cheap material, and then they learn the how to control interface, and then durability has been extended as well. The first report on photochromism, it's done by Dr. Satyen Deb. He's from India, from Kolkata. But then he was working in France. Then he moved to National Renewable Energy Laboratory as director of the Basic Research Center, very long time. He's #1 person still now. He's retired, of course, on smart windows. And I'm proud to say that I was working under his guidance from 2001 to 2003. Yes, thermochromism. It is a type of window that change light reflecting capability in the infrared wavelength range depending on air temperature. The very perspective material is vanadium dioxide, and it changes light reflection capability at about 68 degrees C, and its band gap is 1.68 electron volt. So the problem is to extend its band gap to make it more transparent, and then also to reduce the temperature when light reflection will be light reflection temperature will be minimized. It should be around to about 25-30 degrees C, and solution has been found. And behind these solutions, there are so many research efforts by different research groups from different parts of the world, from Japan, US. And I should say that there is very huge demand and a huge market on that. And there are many companies which are making money from this business. Like Glassview, for example, Labeled Optics, for example, Saint-Gobain, and so forth. There are many of them. Then photochromism. Photochromic materials are quite a lot also in the market, but they are based on polymers and organic compounds with very short durability. Community would like to see inorganic materials that can that possess very durable properties, that can operate within a long time. There are, of course, some photochromic inorganic materials like tungsten oxide and titanium dioxide. And but our material has certain advantage as compared to them in the sense that the existing inorganic materials, when color is changed, color change is accompanied with blocking the visible light. Then a lot of absorption appears in the visible light range, and that's all. But in case of our material, transmittance will be reduced evenly on all wavelengths. So when it comes to far infrared, starting from UV. And there is gasochromic and the piezochromic devices as well. Gasochromic device, they are very well developed as well. So it's about changing color of the material because of gas absorption. Yes. Then I move to mixed anion materials. Why mixed anion materials? Now suddenly change topic. But this is just a different classification of materials. The material that I'm going to talk about, it belongs to this class, mixed anion materials. So this is example of single anion material. And this is example of mixed anion material. When one of the anions or in the system is changed with another type of anion. Okay? And this is not simply a replacement. This replacement is accompanied by huge change in electronic structure, electronic level, and then it will be reflected in changes of the material's properties in general. For example, you see here, this band, EG band, T2G band, it's derived from transition metal elements. They are degenerated. When one of the atoms, anions, is replaced, it will be like split each from other, and that will be reflected in optical properties, in optical band gap. There will be mid-gap states. As a result, by bringing mixed anion materials, we will bring a way of controlling electronic structure of materials, optical properties of materials as well. So, in particular, if this is like electronic structure of single anion material, this will be electronic structure of mixed anion material, and the valence band has been tuned. If valence band tuned, then valence band is tuned, then band dispersion is tuned, then effective mass is influenced, then charge carrier mobility is influenced as well. And in this way, by replacing cations as well, materials property can be tuned. So this is very, very huge field. These are examples of the mixed anion materials which are available today. And Professor Kageyama is one of the world leaders on study of this type of materials. And he will be giving lecture today afternoon. And I strongly recommend to listen to that lecture. And there is one PhD student visiting from IFE who is synthesizing similar different materials, mixed anion materials in Kyoto University. And he will study then evaluate potential of these materials for applications in photocatalysis and in photoelectrochemistry. Now, this is our material. We call it oxyhydride of yttrium. It belongs to mixed anion system. When we synthesized it, we didn't know that this is mixed anion system. So the first title that we ascribed to the material, it was oxygen-containing yttrium hydride. Why is it so? It is, yeah. So let me check. Yes. Yes, it is. The reason is that yttrium dihydride itself. This is a matrix of yttrium dihydride. The blue color atoms are hydrogen ions, and these green color, they are yttrium cations in all system, and the red color ones are oxygen. And this is band structure of yttrium dihydride. When we add oxygen atom, then band gap is opened. So we have provided now phase transition from metallic state to semiconducting state already. And in addition to it, the material will possess certain range of properties that cannot be provided by single anion materials. For example, this yttrium dihydride, it's metal, it cannot be photochromic. And another compound, yttrium oxide, it's not also photochromic, but yttrium oxyhydride, it's photochromic. So new materials engineering, new property, and new applications. Then, of course, when oxygen is entering, local symmetry is changed, then unit cells will be changed, then suddenly it will come to the scene a new research about which phase is more stable. And so a new work will be opened for theories to clarify what the lattice has been formed as a result of the mixed anion materials. And here are functionalities of the photochromic yttrium oxyhydride coating. First of all, it's suppression of glare. When it's very harsh ultraviolet light is coming, then this coating, it will block ultraviolet light so that then the human can watch what is ongoing outside without closing the window. The other one is it reduces the need for blinds, then blockage of harsh ultraviolet light, and then also the material, in addition to blocking ultraviolet light, it will possess some capability to reflect infrared waves as well, far infrared waves as well. This will give added value to the main property, photochromic property. So we started some activity about what is materials capability for air cleaning, for example, and whether the material is toxic or not. Well, I think it's not changing. Yes. So here I would like to say a little bit about the history on the discovery of this material. My PhD student, Trygve Mongstad, so he was studying new materials for silicon-based solar cells. We have deposited aluminum hydride, magnesium hydride. We wanted to bring new materials for silicon-based solar cells. As such, we were interested in materials that contain a lot of hydrogen, because hydrogen passivates a lot of detrimental impurities in silicon, like deep level impurities, transition metal impurities. So then our idea was, why not to use metal hydrides? Because there are so many hydrides, even just 0.01% of hydrogen diffuses and passivates those defects, then all would be okay. But the work about deposition of aluminum hydride, magnesium hydride, it was not successful. Then we moved to magnesium to nickel hydride. More systematic work was done on that. But then instead of bringing new solar cell material, we came to thermochromic and photochromic material. Then we started the work on yttrium hydride. So the day before Trygve was going to take a course on optics, he deposited yttrium hydride. And then I asked him to bring up the sample and do the measurement by using our sample. But then our colleague Augustinus, he said, we don't have time for today. Let's keep your sample. I will do measurement and send you the result. But we asked then, okay, please don't use powerful laser, then you will destroy our material. Then he said, okay, but then luckily he sent this letter next day by saying, sorry, I damaged your material. When illuminated by laser, he was saying it gets dark. So, but luckily he returned the sample back to us. What we did, when we see the material, we found no dark spot. Then Trygve started to check the material step by step by optical microscope. We didn't see any dark spot there, any hole, but what we found is that under action of the light coming from optical microscope, material's color is changed. When we remove it from optical microscope, then it was bleaching. Then we found it's photochromic. And since then, we started to work with this material. But initially, we asked from administration permission to give us at least 1 week to 10 days for publication of this material. And then we again move to study of solar cell materials. And we submitted a paper and it's accepted for publication, publish it. But then we got we were contacted by a company, Saint-Gobain. They were asking, how did you get this result? It's not, we didn't recover it. Then we get surprised. Then we found main know-how, how to date it. We didn't publish it. it was not. So as a result, they were getting contrast of about 10 to 20%, 5-7%. We were getting 40-50%. So then this interest of the company motivated us. We didn't understand why they are interested in this one, not on tungsten oxide, not on titanium dioxide, but on this one. And then it gave us motivation. We started to do some out of working time work. And then, so the projects that I have listed, the first one we got after we published 5-6 journal articles already. And then we did one patent as well. So then, since then, we are moving to today. Now I have about 5-6 patents on this, and one spin-off company has been started. Yes, before us, study of this material was already ongoing. However, different deposition route has been used. So first, on substrate, yttrium thin film was deposited, and then it was encapsulated by palladium. And then yttrium was hydrogenated through palladium layer. But we went in different route. We deposit yttrium in hydrogen atmosphere already, and we get yttrium hydride. Afterwards, we expose it into air, and we get yttrium oxyhydride. This is what we know to today. But when we first get this material, it was always confusing why the material became transparent. The point is, yttrium dihydride, it is black color material, metallic. Yttrium 3 hydride, it's semiconducting with band gap of 2.6 electron volt. Once it's transparent, then it should be 3 hydride. But the hydrogen pressure in the deposition chamber, it's too small. We can hardly reach yttrium dihydride. But in this method, high hydrogen pressures can be provided, and they can get dihydride, 3 hydride, okay. But in this sputtering unit, we cannot get the 3 hydride. So then why band gap is open? So we thought, okay, maybe then oxygen is entering the lattice and stabilizing cubic phase. But it was only postulate, nothing else. And then the other question was where so much oxygen is coming from. Then we were thinking, okay, maybe it's in the deposition chamber itself. Maybe vacuum was not accurate enough. But then later on we found everything is okay with vacuum. In the oxidation, a lot of oxygen is coming from environment, but we found it later on. So this is example of our window. Like half meter by half meter, the deposition unit that we have. Now Vinod Kumar is using this huge machine. It allows deposition on very large area, 0.6 meter by 0.6 meter. This is semi-scalable machine. In industry, they are using 2 meter by 2 meter, very big machines in the glass producing companies. So, this point I mentioned already. Yes. So then in summary, we have yttrium, which is shiny reflecting metal, yttrium dihydride, black, but also shiny reflecting, and yttrium oxyhydride. It's transparent to visible light. And its property, it has unique materials property, like upon illumination, it gets dark. When illumination stopped, and then it's coming back. So if we measure optical properties, transmittance spectra, this is transmittance spectra corresponding to a transparent state. And in the colored state, it's becoming like this. So this is what I mentioned in case of, for example, tungsten oxide. This is light absorption in the clear state, but when it's illuminated, then mid-gap states will be formed that will block visible light. Here, as you see, no blockage of visible light. So in addition to the color change, we found some interesting materials properties. In this paper, we reported everything. We started to do cyclic testing, on, off, because it's not like sun is always on or always off. Although there is one region in Norway, it's called Lofoten or Kirkenes, for example, when half part of the year is sunny, another half part is like dark. So if light is on off, then how this transmittance spectra and would be going on. And since we were interested in solar cell applications of this material, we studied electrical properties as well. The electrical properties, we studied electrical resistance. What we found is that electrical resistivity, it's changing syn phase in synchronically with the transmittance. When the light is on, conductivity is increased. When the light is off, so it was decreasing to initial value. Then, when we analyzed the behavior of the transmittance spectra, this electrical conductivity, what we found is that after illumination is off, it's relaxing within a very long time. This is what we know from the wide band gap materials. It's long term, or persistent photoconductance. So then, if it's persistent photoconductance, if it's correlated with optical properties, then it is we can say it persistent photochromism. Since it's new material, we didn't know mechanism of photochromic effect. Then next my task was to clarify it. How to clarify it? Since mechanism of persistent photoconductance is very well studied in the physics of semiconductors, I wanted to study first persistent photoconductance, the mechanism of it. And we can know something by tuning concentration of anion vacancy. Then I thought, okay, let's then tune hydrogen deposition pressure. Then we will, in this way, control hydride anion vacancy concentration. Then we should see some difference. But when we started to tune hydrogen deposition pressure, we found that transmittance spectra was shifting. But I thought it could be stopped when it comes to band gap of yttrium-3 hydride. But it didn't stop. It started to be shifted toward lower wavelengths as well. It means we are dealing with additional oxidation as well. It means that initial hydrogen deposition pressure is somehow influencing on oxygen amount. Then we published our first article with postulate that oxygen and hydrogen concentrations in the films are anti-correlated. So, and to prove that postulate, we needed ion beam analysis. Ion beam analysis, we did it in the University of Uppsala, RBS, ERDA, and NRA, and that was topic for Ph.D. thesis of Dmitry Moldarev. And so then we showed that the initial postulate is correct. Though by ion beam analysis, we plotted phase diagram. We have established that like materials composition versus materials property, this relationship as well. And then also we have established environmental sensitivity of this material, and then that the material will degrade with time, and we should do something with that. Then let's come back to a little bit on application related story. As I said, in Norway, there is one region called Lofoten, for example, or Kirkenes, when half part of the year is sunny, another half part is dark. So it's not always like sun on, sun off, no. Then what we did, we placed our sample inside glow box with nitrogen atmosphere. Then we illuminated constantly. And then the postdoc, Fredrik Martensen, he was changing his job and he forgot it inside glow box with illumination on. And our engineer found it. Oh, he was saying me something is on site all the time. Can you please check? Then I said, oh, it's our sample. But luckily we didn't pick up the film. What we did is that we left it inside glow box. So when we came at the end of the day, we found the sample is totally dark again. Commonly, when it's dark, within just 10-15 minutes, it will be bleached. But there is no sign for bleaching. Then we were so curious, we left it 1 week. It was not bleaching. Then what we did, we cut the sample into 2 pieces.
one piece we kept like inside the glue box, and the other one we place it outside. Then the one which is outside, it bleached very fast. Within just 20 minutes, it was bleaching. And the one which is inside, it was there. So then we found, oh, this is something very interesting. So we clarified here that lattice is breathing somehow, but we didn't have direct proof for that. Then we were so excited with this finding, but then summer day came, okay? In summer days on July, laboratory is commonly closed. But the other our postdoc, he's now in the University of Uppsala. He wanted to do some experiments in the lab, but he's allowed to do it provided if one of the permanent staff is there. I said, then I will come to the lab. So we were coming to clean room together. One day in the after deposition is finished, we should pick up the sample, but it was already too late. Then we said, oh, let's leave it. Anyway, nobody is using except us. Let's pick up tomorrow in the morning. So, and when in the next day morning we were picking up the sample, we found the sample is totally dark. Then we said, okay, probably we did something wrong. But within, again, 2-3 minutes, it get bleached. Then we found that temperature of the sample is playing here a key role. And that oxygen is coming, in fact, from environment because our sputtering unit, it's not connected to glow box. So this was very like exciting, another finding. Then we see like atmosphere is playing big role. And next, our breakthrough came from Elbriz Murat Baba. He is my PhD student. He defended thesis in 2020. Now he is one of the main manpower in the company Sunfade. And then he brought this light-induced lattice breathing like into effect. So he found that's a reason for that. We addressed it through study of wettability of the material. It was surprising. We studied first wettability, water contact angle, before illumination with UV light. And then what is found is that the water contact angle was around like 100, 110. But after we eliminated with UV, it like it was increased to about 130, 140. So then we found, okay, something is ongoing with the surface of the material. And then after cyclic testing, transmittance in the clear state and in the it was like reducing, unfortunately, but then we found a way how to mitigate it. Then we did this type of prototype windows and we started testing in outdoor conditions. Now we have demo house, a mini demonstration house. And this is now what during cyclic testing we achieved constant transmittance spectra. And yeah. Then by multi-scale modeling, we have predicted possible lattices, symmetries, and so forth, and the studies electronic structure of the solids, and we have plotted phase diagram that has been compared with ion beam analysis. And it was topic for PhD thesis of another my PhD student, Evgeny Strugovshikov. He's now in Spain doing his postdoc. His DFT modeling on structural prediction and like phase portrait, phase diagram, it agrees with the ion beam analysis experiment. So now it's Vinod Kumar. It's his turn to make a breakthrough result. He is already doing it. I hope we will document those results. In particular, he did by DFT modeling, electronic structure study, chemical bonding, optical properties, intrinsic point defects. He's addressing mechanism of photochromic effect by combining DFT with EXAFS, with XPS, and a transmission electron microscope and optical ellipsometry analysis. Okay. This video he already showed yesterday, so I will not show it. This is he's holding the large area glass with photochromic yttrium oxyhydride coating. So he's actively performing testing since November last year in outdoor conditions of properties of the window, and luckily the window is stable. Yesterday he presented the work related to using binders, polysilicon based binders, and polysilicon based encapsulant material. So, and in addition to making thin films, we have developed technology on making photochromic powders as well, and this has been now patented. And we even did more. We have developed ink, and then we have printed out the first photochromic ink, yttrium oxyhydride based. But performance-wise, it's not good enough, so we need a lot of updating here. And then also we developed technology for screen printing of this material as well. Also, there is another work from Germany group, Professor Holger Pohlmann, Holger Kroman, oh yeah, last name I forgot, sorry. He developed the technology on synthesis of oxyhydride of yttrium by chemical method. So we are exchanging our samples. He has sent his samples, but we found that his samples are not photochromic at all. So this will be topic for another project with him. Then also we did, we have performed the structural studies by employing transmission electron microscope. We see the material is polycrystalline, but it's crystalline, and grain size is too small. And we have performed synchrotron analysis as well. We have provided the chemical formula of this material. And this chemical formula has been predicted by us by DFT modeling in 2013. Then first experimental verification of it came out in 2021 only by ion beam analysis by Delft Group. And we also did, before Delft Group, we published it, we did synchrotron analysis, but the experimentalists, they want to stay with this formula. They didn't want to go for that. I don't know. So I accepted their position, but I like this formula. This should be correct one. Then we study work function of this material, and we study photocatalytic properties and the photoelectrochemical performance of this material. And I would like to thank our team, and these are my team from MKU, working with this and with other materials. Yeah, and also our colleagues from IFE and from Institute of Solid State Physics. So thank you for attention, and welcome to ask questions.
So thanks for your nice presentation about the photochromic behavior containing the yttrium hydride. So thank you, sir. And so,
Thank you, Smogul, for a nice presentation and insight into your world. You mentioned the chemically produced materials. They would maybe, if they are in powder form, they would be quite suitable for adsorption studies of water, for instance, and hydrogen, and while film materials are not so easy to do in thermogravimetry. So I just ask, have you tried adsorption studies on these chemical powders?
Unfortunately, no. And very little has been studied in case of powders. We did just compositional analysis and initial testing on photocatalytic and self-cleaning properties, and nothing else.
that could maybe be something for collaboration, because I think
Yes.
we are pretty good at the adsorption at high, the thermogravimetric adsorption studies, but then we would need powders, so we can talk about it.
Yes.
Maybe.
Yes. Mhm.
Thank you.
Thank you, Smuggle, for the new topic for me. I have one question regarding yttrium hydride's structure, chemical composition, which you showed for the neutron diffraction. You said you like the yttrium hydride 3 minus X more than the 2 minus 1. Is it related to the yttrium's oxidation state? Or?
Yes.
Okay.
It's related to oxidation state. Yes.
Okay, so it seems that 3 plus is more stable. That's why that should be the most acceptable formula.
Yes. Yes. Mhm.
And why does the other guys wants the 2 minus delta if it makes sense that yttrium should be 3 plus?
It's I think when it's in dihydride, it's in 2 plus, and oxidation will ongoing until majority of yttrium atoms reach 3 plus. Then we change color. When we illuminate, again certain amount of yttrium we convert from 3 plus to 2 plus, and material gets stuck. That's how we are thinking about it. Then to fit into this way of thinking, I prefer this formula like 3 minus 2x and OX.
Thank you.
Any other question?
Thank you, Smagul. You only presented optical things, optical data.
Yeah.
My question is related to the conductivity of this material. To which extent there is a threshold between electronic and ionic conductivity? Do you have an idea?
We have some very preliminary data, and so according to superconductivity study group, they were claiming that the electrical conductivity is ionic. Then I wanted to measure charge carrier mobility. I was expecting something like polaronic or excitonic conductivity, but that group that has a time of flight measurement system, they said there are no electrons, no holes. We cannot measure it, its mobility. So, and the material was too thick that we have sent. So to be honest, we don't know it yet. But the superconducting group, they were saying electrical conductivity is mostly ionic. But here I have one difficulty. We are presenting as hydrogen ions, hydrogen, with huge size, as Trolls mentioned yesterday. So here I don't have understanding. That's why I was contacting Trolls to help to solve this case. For sure, it's not proton conductor, but if it's huge size hydrogen ions, then how it will be transported? On the other hand, Chinese group, they showed that if material is encapsulated with tungsten oxide, then hydrogen will be diffusing from oxyhydride of yttrium to tungsten oxide and back. Then I just lost totally myself. So if it's true, but on the other hand, we discovered light-induced lattice breathing. When we were encapsulating the material, then we were reducing performance of the material, worsening. That's like similar to clothing, mouth and nose, then performance was decreasing. But Chinese group, they succeeded it. Then also Netherlands group, Bernard Dam's group, they have one PhD student, I was opponent on that. They have encapsulated with silicon nitride deposited by ALD. They are also claiming that it's material is surviving, it's working. So I'm here in this case just totally lost. And many things are, unknown as to ionic transport.
Thank you.
Yeah.
So any other question? No more questions, means we can close this session. So once again, I thanks organizing SWAP 2023. So once again, thanks to Dr. K.S. Magal to wonderful presentation. Thank you, sir.
Thank you. Thank you so much, sir, for sharing your deep knowledge with us. And I thank Dr. A. Siva on behalf of the SWAB organization team for serving as the session chair. I would like to invite Dr. A. Siva, sir, to honor our chief guest, Dr. K. Smuggle, with the momentum. Thank you, sir. I would like to invite Dr. K. Anita, ma'am, to honor Dr. A. Siva, sir, with the momentum. Thank you. Now it's time for the deep break. I would like to request all the guests and participants move towards the CVR hall outside. Tea is waiting for you. We will resume after 15 minutes. Here. Welcome back to the Invader Section 2. I would like to invite Professor Murugesan, Chairperson of School of Chemistry, Madurai Kamaraj University, upon the stage as the section chair to lead the section by introducing our invited speakers, Professor Hiroshi Gajiyama, Kyoto University, Japan, to our estimate audience.
Good afternoon. So I'm happy to be the chair of this session again. So the speaker of this session is Professor Hiroshi Kiyogama from Kyoto University. He's going to deliver topic schedule. So the lecture in this session will be delivered by Professor Hiroshi Kiyogama from Kyoto University. He will be talking on novel topochemical reactions toward mixed anion catalysts. And for want of introducing the speaker to the audience, we have already displayed our achievements and academic activities in the display. Just one of some of them I will just read out. He has received his Ph.D. from Kyoto University in the year 1998, and he is an associate professor from Ueda University, Tokyo, for 5 years. And then from 2003 onwards, he became associate professor in the Department of Chemistry, Kyoto University. From 2010, he is serving as full professor at the Department of Energy, Hydrocarbon Chemistry, Graduate School of Engineering, Kyoto University. He is also an adjunct professor at Institute for Integrated Cell Material Sciences, Kyoto University. And he is editor of Inorganic Chemistry since 2017. His research interests mainly on novel chemical and physical functionalities like photocatalysis, magnetism, and superconductivity of inorganic compounds. In particular, his recent strong emphasis is on development of functionalization of mixed anion compounds such as oxyhydrohydrides and oxyhalides. Is one of the paper is a highly cited review article in the Nature Communications published in 2018. He, to his credit, he has over 400 papers and patents, and including Nature, Science, Nature Materials, Nature Chemistry, Nature Communications, and Journal of American Chemical Society, and Adjuvant Chemistry, and also Inorganic Chemistry. So he has received various awards, including Research Award for Young Scientist in the year 2001, and Young Scientist Prize in 2007, and Young Scientist Award for the Physical Society of Japan in the year 2017. And the list goes on, and you can read from there. And now, with this brief introduction, I leave the professor in front of you for his lecture. Professor Hiroshi, please take over the stage. Yes, Professor Hiroshi, your voice is not audible. இல்லை அவர் மைக் ஆன் பண்ணியிருக்காரான்னு தெரியலையே. அங்கே அதில் அந்த நெக்ஸ்ட்டில் இது பண்ணுங்க. அவர் மைக் ஆன் பண்ணியிருக்காரா பாருங்க. மைக் ஆனில் தானே இருக்கு. ஆ இல்லை, இங்கே அதில் இருக்கு. இல்லைப்பா, அது இல்லை ஆடியோ எதில் கனெக்ட் ஆகிருக்குன்னு பாருங்கள். இந்த நம்மளோட ஆடியோவில் போயிட்டு ஒருவேளை வேறு நம்ம ஆடியோ வேறு எதுலையாவது இருக்கும். இல்லைப்பா, இங்கே ஆடியோ இருக்கு, நம்மளோடது வேறு எதுலையாவது லிங்க் ஆயிருந்தாலும் இருக்கும். இல்லைன்னா அதை விட Professor Hiroshi, we are not hearing your voice. Could you please leave the meeting and then come back again, join again? நம்ம வாய்ஸ் அங்கே கேட்கலையே. இல்லை போயிட்டாரா? இருக்கார்ல, இருக்காரு அதில், அந்த இருக்கு, அது கீழே இருக்கு, அது கீழே இருக்காருல்ல, அது கீழே, அது கீழே. இருக்காரு. Professor, we are not hearing your voice. அவரோடது இதில் மியூட்ல இருக்கு. அவரோடது அவரோட மைக்கை பார்த்து மியூட்ல இருக்கிற மாதிரி இல்லையா? மியூட், அவர் மைக் மியூட்ல தானே இருக்கு. சார், ப்ளீஸ் switch on your mic. Your mic is in mute. அந்த இதுல வைங்க, இந்த மோட்ல. ப்ளீஸ் அன்மியூட் யுவர் மைக். யாருக்கு? அது அவருக்கேவா?
Okay.
Yeah, now its voice is coming.
Can you hear me?
Yes, Professor. Yes, Professor. Yep, please share your presentation and go ahead, Professor.
Yeah, I'm muting. Yeah. Can you hear? Okay. But I don't know what does it mean. Then I wish to share the screen, but I'm not sharing. It's okay. I think you can open the presentation. So, maybe can you ask?
Yes. But how to? あれなんだろうこれ。
So strange. You have YouTube somewhere. You have YouTube on. Because there is the.
This. What wrong with this? So maybe do this?
Here, maybe this. And this is just screen. No. Can you press again?
No.
No. There's
This one.
yeah, but the first one.
Yeah.
Yes. Okay. Here, we need to close this.
Alright.
Screen.
Then,
Yeah.
but
The lower one. Yeah.
so
Okay. Press the center button. Yeah. I think now it's showing. I think. Maybe here. Okay. Or does it mean
oh my god.
this? Yeah.
No, it's showing this. Open the PowerPoint.
Yeah.
Then,
Wait a second. I will bring my laptop so we can see.
the entire screen first. And share.
Yeah. So it works like this. Present a window.
Maybe my computer. Okay. Maybe I should. I'm asking, so I have problem of showing my slide. So I'm asking Artem to use his
Professor,
computer.
Professor, just Professor, 1 minute. We will show how to share that. Please follow the steps, please. Good. Professor, please follow. Please follow that how we are just doing. You go to here. You please click and a window, and then you click. Like that. This window. Then you share. And you come to this page
They're showing how to do.
like
They
that.
know already how to do this on your computer. I don't know why.
இது வேணும் Others stop sharing. Okay. Professor, please again. I will do. Professor, just I will show that. Please, you go to this share button and then click a window. Our entire screen போட்டு போடுறாங்க. Professor, you don't click entire window. Please follow this. Just click a window and then click this window button and just share. அவரு அப்படியே போட்டுட்டு இருக்கு.
Not yet.
அவர் இங்க கேட்க மாட்டேங்கிறாரு சொல்றது.
Maybe you go to your office. But it's maybe not connected.
Professor Hiroshi, just 1 minute. Could you follow the steps what I am following? Professor, could you listen?
Yeah, my problem is maybe my computer doesn't work, so I'm just copying my slide to.
No, Professor,
my student.
no, it's not, Professor. Professor, you are sharing the entire screen. Not necessary. Just share a window. Just you follow like this. Click this and click a window, and then click there. Put the share.
Okay, it's okay.
அவர் அதையும் செய்ய மாட்டேங்கிறாரு. அதை கேட்க மாட்டேங்கிறாரு அவரு.
So this.
அவர்கிட்ட சொல்லிடுவோம்.
It's
working, but because the presentation.
Okay, Professor. Shall I go with the next presentation? Maybe 20 minutes. You can shut out that. I will come back again.
Oh, now it's working.
Is it okay?
Let's see.
Oh, it's okay.
Yeah, it's right.
Maybe. Yeah. So this is your.
Yeah. Okay. You can speak there and show here.
All right. So I hope you can hear me. Yes.
Yeah.
Okay. So I'm very sorry that this problem, which is because of my computer. I ask now Artem for using his computer. So once again, I'm sorry that I cannot attend this symposium in person, but I'm happy to share with you with my recent research on mixed ion compounds and reactions. So, okay.
Maybe I could just stay here somewhere.
Okay, so my talk will discuss recent discovery on topochemical reactions, which is shown here. If I, two papers. If I have time left, I will discuss the third one, which is not topochemical reactions, but related to the second topic. Right. So, okay, maybe you are not familiar with topochemical reactions. So I'd like to briefly introduce what topochemical reaction is. Topochemical reaction is a reaction, low temperature reaction basically, for which you can compare the structure. You can relate the structures before and after the reactions. Maybe most famous example is this lithium intercalation into graphite. You can do this chemically or electrochemically as you use in your mobile phone. So yeah, as you can see, lithium can be intercalated with some staging behavior. Another example shown on your top left is the topochemical reaction using the iron oxide with peroxide structure. By using calcium hydride, you can eliminate so-called apical oxygen to produce the strontium iron 2, bearing the square planar iron coordinations, which is very rare. So, but in this particular case, the oxygen vacancy is created along the 001 direction. But our recent finding, topochemical reactions shown on your bottom left, is the another example where the oxygen vacancy layer is created along 111 direction of the peroxide structures. And the last example shown in the bottom right is the topochemical reactions changing the alkali atom from rubidium, showing the P-type structure, to potassium, the orthorhombic A-lattice structure, and the lithium case with the I-centered lattices. Okay. Anyway, you can, by doing before and after reaction, you can compare the structures of the host and the daughter compounds. Right. So experimentally, what we probe such topochemical reaction is the first thing is to perform powder X-ray diffractions. So this is from the review paper on graphite intercalations. You can see some staging behavior. The X-ray diffraction pattern changes in this way. So you can identify what intercalations happening or the intercalations happening. And same is true for the perovskite type oxide. In the first example, the top example, you see that the cubic lattice, the blue one, change into the red one, showing the actually the red pattern can be indexed by the tetragonal, splitted peaks. Okay, so you can see the similarity between the diffraction patterns after and before reactions. The same thing is happening for this vanadium oxynitride material before and after the reaction. Some superstructure occurs, but basically the crystal structure looks like the same. Okay, then you can maybe reduce the expected structures of the after the reactions. So speaking about mixed ion compounds, already the previous speaker, Smagu, introduced mixed ion compounds. If you are not familiar with the mixed ion compounds, you may take a look at this review paper published about 5 years ago. But we are now planning to publish the textbook of mixed ion compounds through RSC. We published last year, 2 years ago, the Japanese version, but now we are translating into English. Or you may take a look at a book chapter of the mixed ion compounds in the recently published, inorganic chemistry textbook from Elsevier. Okay. Anyway, regarding on the hydrogen, maybe you are familiar with the protonic type of hydrogen because considering the environment of the Earth or our human bodies. But hydride anion introduced by Smagu already is very unique ionic state of hydrogen. And this is still very simple, maybe most simple anion with only 2 electrons, but nevertheless, it may be showing the most exciting phenomena of our functionalities. Then in the previous example of topochemical reactions of iron perovskite, I showed the structure conversion, but in this case, oxygen are only removed. But in this, the second example, this barium titanium oxide, in addition to the oxygen removal, the hydrogen or hydride ion are inserted into the structure with this calcium hydride reactions. Okay. And as I said, the hydride anion is already very interesting because it is unstable compared to the proton. So you may expect that some interesting functions from the oxyhydride material. Oxide is very famous, very good, advantageous for being the very stable material. But maybe with introduction of the hydride, you can keep the stability of the material, but introduce the activities of some new functions. Actually, this happens in this material. Okay, so now we actually already observed that this material, the oxyhydride, has the ability to cleave the HH bond in NH2 molecules, and also independently we observed that the nitrogen molecule with triple bond can be cleaved as low as 400 degrees C. Okay, this is just chemical reactions, but when we flow H2 gas and N2 gas at the same time, we observe that the ammonia is generated, as you can see from this panel. So in the case of oxyhydride, also oxide material, the precursor material, this doesn't generate any ammonia gas. But when we use the oxyhydride material, the flowing H2 and N2 give you the ammonia with very high efficiencies. Okay. Then, from a fundamental point of view, we found that this is very unusual discovery because titanium was regarded as a dead element in the field of catalysis, which can be seen from this volcano plot. Volcano plot is showing the bonding. Horizontal axis is the bonding with metal nitrogen, and you see that the highest activity is obtained for the iron or ruthenium. But because titanium, as you can see from the right figure, titanium has the very strong bonding with nitrogen. So, this means that this cannot be good catalyst for ammonia synthesis. But as you saw in the previous slide, that our material shows very efficient ammonia catalyst reaction synthesis catalyst activities. So we say that the introduction of the hydride anion into the structure breaks the scaling rules. So motivated by this discovery, my former student, actually the current postdoc, Yu Kao, she did some catalytic test for other hydride-based material, for example, titanium H2 or vanadium hydride and so on, and observing similarly the very high activities. Okay. Then she extended this study. Extended this study to a chromium-based material because this is also early transition metals. Then we expected similar high activities for ammonia synthesis catalyst. Okay. Then we found that actually we happened to find that this calcium-3, chromium nitride 3, are showing very nice catalytic activity comparable to this titanium oxyhydride. Okay. But after the catalytic test activities performance, we tested the sample catalysis, this nitride with X-ray diffractions, and finding that this material crystal structure has changed. So before this reaction, catalysis test, the crystal structure is orthorhombic with these lattice parameters. But after reaction, the X-ray diffraction pattern can be indexed with hexagonal pattern with A-axis of 7 angstrom and C-axis of 5 angstrom. Okay, so some crystal structure has been changed. Okay, but in contrast to the the example I show for topochemical reactions, maybe you cannot we couldn't rationalize these crystal structural changes. Then we collaborated with Artem Abakumov, who is an excellent expert of the transmission electron microscopy and structure analysis. And we found out that the crystal structure looks like this. Okay, we use the TEM and the synchrotron and neutron diffractions, and we solved the crystal structure. And we found that the hydrogen also included in the structure. So it is hexagonal phase. It's not nitride, but nitride hydride. Okay. Then this showed the how crystal structure has been changed through H2 annealing. Then we found that the relation between these two structures. In precursor material, the nitride orthorhombic structure are composed of the kind of lock-out block, the 1 to 2 unit lock-out chains are formed, and these chains are bridged by the chromium N3 unit, which is in purple. Okay, but after the reaction, these 2x1 lock-out chains modify structure and change into the hexagonal chain, or octahedral chains, as you can see here. But this chromium N3 triangle unit doesn't change. Then, so this shows the movie showing how crystal structure is transforming from the initial orthorhombic structure to the hexagonal structure. Okay, as you can see from this movie, this is kind of transformation is mimicking the hinge tessellations. Okay, so actually the triangle unit doesn't change, but this lock-out chain transforming into the octahedral chains. Okay, so this is unusual topochemical reactions. Okay. Then we did some further analysis and experiments and finding that the phase transformation with the hydrogen or hydride insertion occurs in a biphasic phase. So actually, we didn't find any intermediate phases. Okay, so by measuring the X-ray diffraction institute, we found that the only ratio between orthorhombic phase and hexagonal phase changes. Okay, and another observation is that when we make a heat treatment of the hexagonal phase under vacuum, the hydrogen is deintercalated with other gas. Then we have an initial composition, same composition as the initial material, calcium-3, chromium N3. However, the structure doesn't change into the original orthorhombic structure, but stays hexagonal, which means that the hexagonal orthorhombic chain is remained. Then the FT calculation and other things shows that the electron is located in the hexagonal void by the calcium 6. Okay, so this is regarded as an electrolyte material, if you like. Okay, so now we know that in this hexagonal material, the H or without H, the actually hydride anion is migrating in the structures. Maybe this is very important for considering the high catalytic activity during the catalysis performance. Okay. Now, previously we demonstrate that this titanium, barium titanium oxyhydride, the hydrogen migration through the lattice is playing an important role in this catalytic activity, because the hydrogen can be regarded as poisonous, giving a poisonous effect, so-called hydrogen poisoning. But hydrogen migration in this catalyst is, avoiding such problems. So maybe we may think that these compounds, this hydride nitride compounds, is showing similar advantages. Namely, hydride can migrate, and this can avoid the problem of the hydrogen poisoning. Okay, so then we expect that the maybe hydride, maybe nitrogen directly come into the this hydride and react to form the ammonia gas. But unexpectedly, our DFT calculation and so on revealed that maybe the reaction pathway is different. So we found, actually, to make story short, we found that in this triangle unit, I mean the chromium N3 unit, that is the most important part of the structure. Then first, the N2 molecule is attached into the center of the triangle. Then H2 gas is attached to the top side of the dimer, then finally forming the NH3. So this is so-called associative pathway. But anyway, we observe this type of interesting reactions together with the important catalytic activities. All right. So in this first part, we show that the ammonia synthesis catalysis, and which is given by this concept of the anion diffusions and reactions. But in the second part of my talk is based on this concept B, which is the band gap controlling with mixed anions. Okay. So the concept is very simple. Actually, by oxide has normally a wide band gap, and could be transparent with the visible light. But by using the different anion with less electronegativity, such as the nitride 3+ and chlorine minus, you may reduce the band gap by putting the 2p orbitals of different anion on the oxygen 2p orbitals. Okay. And this is actually possible with this bismuth niobium or tantalum oxy halides material we actually reported 7 years ago. And you see that this yellow color showing the reduced band gap. And actually, this shows very stable visible light for catalysts. The actually problem of the mixed anion compounds is that instability against the photo-generated holes. But somehow this material is very stable against the photocatalytic reactions. Anyway, the structure point of view, actually most important part of this structure is this bismuth 2O2 layer. And actually, this is acting as an important unit for catalytic activity. But anyway, after this discovery, 4181 compounds, we found the series of the similar type of compounds, which is summarized in these papers. But anyway, by changing the composition, the combination of the structures, we are able to control the conduction band maximums. Okay. Then question is, what happens when we increase the number of layers in this double layer, bismuth 2O2 layer? Actually, there are only a few examples of having the triple layer, I mean the bismuth 2NO4 layer. Okay, so this was reported about 20 years ago. Then we found that these compounds shows the ability of the controlling the valence band, as you can see here. But I don't want to go into details, so you may take a look at this Jack's paper published about 2 years ago. But anyway, on the course of this characterization of the structure, namely in this bismuth material, okay, we found the unwanted the impurity phases. So this was a problem in the initial stage of our researches. But after that, we focused on this material, and actually we tried to find this material structures. Then we found that this material, the unknown compounds, has a lattice parameter of the C-axis of the 35 angstrom, which is nearly half of this tri-layer systems. So we speculated that this material has 6 sect pool fluoride type structures. Then we got this composition, and later disappointed to see that these compounds is already reported about maybe nearly 40 years ago, okay, in this paper. And recently, somehow, this material, without structure, without knowing structure, this material was found to be very nice photocatalysts, as you can see in these papers. Then we decided to tackle on the crystal structure. And as I said, that this compound has a very long C-axis and tetragonally indexed. But after single crystal or powder diffraction measurement, we found that the basic structure is okay, but actually the structure is much more complicated. For example, in this single crystal X-ray diffraction patterns, you see a lot of peaks. Actually, this cannot be indexed by using simple superstructures. Okay. Then once again, we collaborated with Artem Abakumov about who uses the TEM, and actually he observed this wavy behavior in the crystal structure. Then by using this incommensurate type modulations, he was able to solve the crystal structures. Okay. Then we found this is the final crystal structure. So as I mentioned, this structure we thought that this structure should have a 6-layer of fluoride block, but we found that this is not pure fluoride structure, but mixture of the fluoride structure and the lock-out structures. As you can see here in this orange region, the kind of lock-out block, a kind of one-dimensional block is inserted in this 6-layer fluoride structures. That's why this gives rise to the modulation of the crystal structures. Okay. Yeah, but thinking about the photocatalysis, maybe such a wavy behavior is not so good. Maybe you can see from this cartoon, the wavy things maybe is very bad for photogenerated holes, photogenerated electrons. Maybe flat surface, flat layer could be ideal for photocatalytic activities. Okay. Then we wanted to consider some chemical reactions to remove such modulations. And in fact, we did the oxygen fluorine anion exchange reactions. It's 1-2 anion exchange reactions because of the charge neutrality. But anyway, after this treatment, we observed that the modulated or corrugated block become completely flat. And luckily enough, we obtained the enhanced the carrier dynamics. Actually, by doping or exchanging fluorine, we are able to see the improved carrier dynamics and also catalytic performance. This is some organic molecule degradation test, but we observed that for the fluorine exchange sample, the catalytic activity is significantly enhanced. Okay, so we are very happy about this. But the remaining problem is that the little refinement. we did synchrotron diffraction and Newton diffractions. And synchrotron diffraction seems to be okay because of the difference seems to be okay. But Newton diffraction has large deviations from this expected modeled the perfect fluoride layers. So something is going on. Then finally, we found that this structure, our expected structure is not correct, but we found that sorry, this was, yeah, so this is also this is a final structure. So now instead of the perfect fluorine structure, we found that actually this is the alternating stacking of the fluoride layer, locks out layer, fluoride layer, locks out layer, fluoride layer. So such alternation along this C-axis appear in the final compounds. Namely, by doing topochemical fluorinations, the crystal structure with the locks out and the fluoride unit are changed from this modulated structure to this alternating stacking layer structures. Okay. So I maybe time is running, but maybe I'd like to briefly discuss about our recent finding. Actually, the story is nearly the same. We wanted to develop the new photocatalyst. As I said, the electronegativity is an important parameter for tuning the band gap. So the chlorine system, namely chlorine system, should have larger band gap than bromine system, because bromine has the less electronegativity. So we thought that maybe we should prepare this unreported compounds of iodine-based material. Iodine has less electronegativity. And in fact, we observe in this red curve that the band gap is strongly reduced. So we expect that this 4,5,2 material, antimony 4, oxygen 5, and I2 compounds should be obtained. Okay. However, we couldn't index the X-ray diffraction patterns. And from the diffraction from TEM pattern, we found that the cluster-like unit in the structures and the lattice parameter seems to be much larger than the originally expected compounds. Then, then we finally solved the crystal structure. And in fact, this material has more than 800 atoms in the unit cell, so which is completely different from our expected crystal structures. So this is not topochemical reactions, but some unexpected, serendipity, Lipschitz type discoveries. Okay. Then this is the crystal structures of the final material. This light blue is showing the positively charged large clusters forming the FCC unit cell. But this is unusual because most of the cluster type material has the negatively charged clusters such as Kekin type or Anderson type or Dawson type, as you can see in these cartoons. And there are thousands of papers showing some functions. Okay. But in our case have no different. It's negatively charged, positively charged, clusters. And interestingly, we found that in this positively charged cluster, there are some protons on the surface of the cluster, and this proton are highly acidic, and they are showing very nice catalytic activity for acid type reactions such as the pinnacle rearrangement reactions and so on. Okay. All right. So this is the summary of my talk. So I hope you are convinced that the topochemical reactions is very interesting in terms of the creation of the new materials, especially the mixed ion compounds. And I show several examples of the catalysis or photocatalysis, but actually application could be diverse, including superconductivity or other functional properties. So finally, I'd like to thank my colleagues, especially for the first topic, you saw, Yoji Kobayashi, who is associate professor in the KAUST, Saudi Arabia. And the second topic was mostly done by our assistant professor, Daichi Kato. And finally, I'd like to thank my group members and thank you for you, the audience. Thank you very much for your kind attention. Thank you.
So now, one or two short questions for want of time.
Hi, it is Truls Nordby here. Nice to hear your talk. Can you hear me?
I can hear, but it's very difficult to.
It is Truls here, Truls Nordby. You said that hydride ion and electron interact during transport. Does it mean that you now believe that diffusion can take place by hydrogen atom or proton?
So you're asking about the first topic, right?
About the diffusion of hydride ion. Can it take place by hydrogen atom and electron together?
Yes.
Thank you.
Yeah, hydride should have negative charge, so it has 2 electrons. So I don't catch your point.
We can take it on email later.
Yeah, sorry. Problem is that I cannot hear the.
The professor is asking whether the diffusion of hydride ion takes place with electron and hydrogen.
Yeah, I think, yeah, it's experimentally confirmed, but I expect that the hydride ion should, migrate as a hydride, but yeah, maybe there are some, electron leaving into the other, maybe chromium or other places. I think such an maybe unusual diffusion process is,
Yeah, thank you.
Yeah, there might be such a possibility.
Yeah, thank you, professor.
Yeah, but basically, in this octahedral chains are composed of the calcium, which is highly electropositive. So, yeah, maybe hydrogen should be comfortable with H- species. But during maybe migration, such unusual, maybe maybe dissociations or something might happen.
Okay, thank you, professor, for your nice presentation on nice work. Thank you, professor, for joining.
Thank you very much, and sorry for these problems of my presentations. Thank you.
So now the next presentation on this session will be by Dr. Kalpana Singh from University of Oslo. She will be talking on positrods for proton ceramic electrochemical cells. And due to short time, and I will introduce only short achievements of her. She has completed her Ph.D. from University of Calgary in the year 2016, and then she has worked as a postdoctoral fellow in the Department of Chemistry, University of Calgary for 2 years, 1 year. And then she was a visiting scientist in Israel Institute of Technology for about 3 months. Then she moved to as a Canada First Research Excellence Fund postdoctoral fellow, and she worked there for 2 years. And then again he worked on MITOX Accelerated Industrial Postdoctoral Fellow in the Department of Chemistry, University of Calgary from 2010 20 to 2021. And from November 2021, she's been working as a researcher in the Department of Chemistry, University of Oslo. And she has published many papers and guided many MS theses. And with this small introduction, I request Dr. Kalpana Singh to deliver a lecture on positrons for proton ceramic electrochemical cells. Because of short time availability, I will ask her to present in 20 minutes, possibly.
I will try to finish in 20 minutes for sure. Thank you. So good afternoon, everyone. I will try to keep it short because everybody wants to go for a lunch. But I will try to make sure that in next 20 minutes, I keep you engaged and you can get some more information about positrons for proton ceramic fuel cells and electrolyzers. So the outline of the talk is very simple. We will see why we need to study proton ceramic fuel cells and electrolyzers. What are positrons and why we are trying to understand them, and the effect of applied biases on the polarization resistance, and what is the need to study this kind of topic. So as the name suggests, proton ceramic fuel cells and electrolyzers are electrochemical devices which contain ceramics which conducts protons for both electrodes and electrolytes. So here, the overall reaction is the combination of hydrogen with oxygen to form water, which can happen at OCV in both directions. So in the fuel cell mode, what we have is we have anode and cathode. In here, hydrogen gets oxidized, releases electrons and protons travel via the electrolyte towards the cathode and combines with oxygen to form water. And the electrons travel through the external circuit and give electricity. Now, if we reverse the reaction in the electrolysis mode, so if we reverse the reaction in the electrolysis mode, what we have is that the cathode becomes the anode and the anode becomes the cathode. So here in the anode, in the oxidizing medium, we have a formation of protons which travel through the anode via the electrolyte towards the cathode, and there's a formation of water. Given that we go from anode becomes cathode and cathode becomes anode, there might be a confusion in the terminology. So in order to keep things simple, we can call the negatrodes and the positrodes. So negatrodes and positrodes terminology is consistent in the both systems. And these positrodes are always in an oxidizing environment, and this is a very complicated reactions which happen at positrodes. That's why we need to study the positrode materials. So now, given the definition that we know what are positrodes, we can move towards the next topic, which is materials for positrodes. So typically, most of the studied materials in the literature are based on simple perovskites and double perovskites. So in the simple perovskites, what we have is barium, strontium, lanthanum at the A sites, and the transition metals, which are typical iron and cobalt at the base site. Similarly, for the double perovskites, we can have barium, strontium, and lanthanides at the A sites and cobalt and iron at the B sites. So both these materials have been studied widely to act as a positrodes for proton ceramic fuel cells and electrolyzers. So in today's talk, the main example which we're going to see is the barium, lanthanum, cobalt oxides, which are simple cubic perovskites, and barium rare earth transition metal oxides, which are double perovskites. So yesterday, Truls has beautifully explained how protons get introduced. So here I will again go through the introduction of protons into the ceramics, just to refurbish what we learned yesterday. So here in the A reaction, what we have is a simple acid-base reaction where there is a dissociative water incorporation. So water from the atmosphere gets absorbed at the surface, forms OH minus, H plus. So one OH minus goes and sits at the empty vacant sites of oxygen, and the other, the H plus goes and combines with the oxygen. In this way, what we do is we form two protonic defects. The next reaction to see is dissociative oxygen incorporation, which is a redox reaction, where what we see is oxygen comes from the atmosphere, sits at the surface, dissociates, and oxygen molecules goes and sits at the empty vacant site. But because it needs some charge, it takes electrons from the transition metals such as cobalt and iron, and hence the electrons are lost from here, and we form holes, which can lead to electronic conductivity, which can be explained by this Kroger-Wink notation. Next reaction is a type C reaction, which you can say that is a combination of A and B reaction together, which is called as hydrogenation reaction, where proton is incorporated in the material at the expense of electron holes. So water comes from the atmosphere, oxygen leaves, and the protons go and attach to two oxide ions. And when oxygen is leaving, it gives the electrons to the already existing holes, and hence we eat up the holes. So here we can introduce protons even if we don't have the oxide vacancies. So this part is called hydrogenation reaction, and it is important to remember this one because we will see examples in some next slides where we see that even though some of the materials did not have oxide vacancies, they still showed some better performances in the electrochemical studies. So since we are trying to understand the positrodes and we want to understand the hydration and redox properties, it's very important to see some of the TG results, which are very simple experiments but give us very useful information. So here we have 4 types of materials. This is the oxygen non-stoichiometry, which is missing here, is 6 minus delta versus temperature. What we see here is that the red color sample, which is BGLC, it's shown in the red plot, shows the highest oxygen non-stoichiometry. That means the lowest amount of oxygen and high oxygen vacancies. Next, because of the short time, I will move to the main important thing, which is to understand the hydration properties. So now let's take all the materials, do a TG where we are going to monitor mass change with time. And what we see is that when we have a dry atmosphere at temperature 400 degrees Celsius, PO2 of 4 into 10 to the minus 4 atmosphere, we don't see a mass change with time. But the moment we switch to a wet atmosphere with the pH2 of 0.02, we see the BGLC, the red color sample, showed an increase in weight. This indicates the hydration of the BGLC material. Given that if the hydration is happening just because of the filling up of the oxygen vacancies, we can calculate the moles of protons per mole of BGLC. For this particular sample and this atmosphere, there is 0.03 mole of protons per mole of BGLC. So here we saw that how we can correlate the oxygen non-stoichiometry with the hydration materials in the TG. Next is to see if we have different types of transition, different types of lanthanides, what we're going to see. So this is a case of a double perovskite sample where in the lanthanide position we have dipsium, terbium, gadolinium, samarium, neodymium, praseodymium, and lanthanum. So here the main things to see is that the gadolinium and lanthanum sample showed the weight gain when we switched from dry condition to the wet condition, and there is about 0.021% weight gain for the gadolinium sample and around 0.016 percentage weight gain for the lanthanum sample. But interesting things to see is that when we switch back to dry condition, the weight does not come back. This means the increase in weight is irreversible. Now, when we compare the simple perovskites with the double perovskite, what we see is that barium lanthanum cobalt oxide, which is a double perovskite, showed the highest, more weight gain of around 0.016% versus BLC, which is a simple cubic perovskite, and it showed only a weight gain of 0.04%. So this indicates that a double perovskite, which has high amount of oxidant vacancies, leads to high hydration. So in terms of that, if we use double perovskite in electrochemical performance, they should show a better performance compared to BLC. So now, as I said, there was an irreversible weight gain. This might be related to the change in the structure while hydration is happening. So the structure changes when the proton is getting introduced. And if you want to know more about that part, this is a paper recently published last year in Dalton Transactions, which talks all about the hydration in these samples and the structural changes and what is the reason there is no weight gain, weight loss after switching from wet to dry atmosphere. So as I said, we are going to study these materials as the positrodes for the electrochemical cells. It is important to see how we want to study them. So this is a probostat, typical diagram of a probostat from Truls Norby's company called Norex. Here we can see that sample is placed in between, and we have a working electrode on the top and the counter electrode at the bottom and a ring to connect the reference electrode. And this is top view for the bottom side of the sample, where we have reference electrode here, counter electrode, and on the other side we have the working electrode. And this is a typical SEM images, which are very typical, which should be the case, which is thick electrolyte, dense electrolyte, very porous working electrode in order to have a proper gas transport. Next is to see the polarization resistance of the BGLCs. So I'm assuming that everybody is very well versed with the Nyquist plots. So this Nyquist plot just says that we have two electrochemical processes related to the polarization resistance. And if we plot the RP versus temperature, what we see is that the BGLC, which showed the highest hydration, is also showing the lowest polarization resistance. But one thing important to see is that the praseodymium, which did not show any hydration or very low hydration, is still showing almost similar RP values at low temperatures. So this indicates that maybe we need to understand more about how many protons are needed to have a better performances in these kind of systems. Next, if we change the PO2, we can understand more about the system, where here what we see is that if we go from high PO2 to the lower PO2s, the RP decreases. For example, which is very usual, that you are decreasing the reactants, you are decreasing the oxide ions, so the RP is decreasing. So now we only saw the RP versus temperature, which is very typical, but it's very important to deconvolute or try to understand the three charges which are involved in the material and how they contribute towards the polarization resistance. So as we know, both electrode and electrolyte are triple conducting. They can conduct three types of charge carriers. It is very important to understand how they are connected in rails. So this is a very simple rail model where we show that the electrolyte resistance of the protons, oxide ions, and holes are connected in parallel. And then we can calculate the resistance for this system via this equation. And we can model the data, but the first step to model the data is to do an experiment in wet argon. So this is the conductivity versus temperature in wet argon atmosphere. And then we can model the data and we can get the proton conductivity and the oxide ion conductivity, and the very little p-type conductivity. So all the dashed lines are the model data, and the open symbols are the experimental data. Now, taking this as a base for the p-type conductivity, the difference in p-type conductivity between the wet air and the wet argon, we can fit the data and we can model the data to get more information. And here we see that the oxide ion conductivity and p-type conductivity has been modeled, and they are much higher than the wet argon atmosphere. So once we have done the electrolyte part, we can move towards the electrode part, where we have the RP1, which we at present we are going to call mixed mid-frequency RP, because this is occurring around mid-frequency, and we will fit the data with the model where we have protons and oxide ions for the mid-frequency sample, and the protons and oxides will resistances will be fitted in this equation. Also, we can relate the this parameters with the rate equation, where we have the dependencies with the PO2s, PH2Os, pre-exponential factors, and activation energy. And by doing that, we can have proper fits of the log R versus temperature. Here we can easily see two activation energies related to proton, positive effect of proton conduction at low temperature, and this is related to oxide and conductivity, and also a bit of p-type conductivity at high temperatures. So by using this model, we can fit the data and we can get contribution from the protons and oxide ions just for the mid-frequency process, and we can model the experimental data. Next, we can do the similar thing for the low-frequency process, and now we just need to fit the low-frequency resistances in the whole model, and we can again fit the low frequency and data for the protons and for the oxides. And by doing this, we can get the activation energies and pre-exponential factors from the modeling. So the purpose of showing this modeling data was to show that if you can model your data, you can get more information and calculate the individual contribution of each type of charge carrier for each type of polarization process in the positrodes. Now, I will really rush through these slides because we have less time. But if we look at the reaction at positrodes, this is well known that if you have a platinum, for example, as a positrode, which does not have sufficient proton conductivity, the reaction will be limited to the triple phase boundary. And if you have positrode material with high proton conductivity, the whole electrode surface area, electrode will be active, and you will get a better performance in terms of electrochemical performances. So again, we have seen the reactions at positrodes, and in the fuel cell modes and the electrolysis mode, we can have the reactions. And these are the some of the elementary steps which are very complicated, but here they are shown in very simple ways. We have the mass transfer, dissociation, charge transfer of protons, mass transfer, and the proton transport and desorption. So the reason for showing this slide was to say that if the reactions are very complicated, there are many resistances, many electrochemical processes, the fitting of the data is very complicated. So this is also a very simple Nyquist plot where we can fit the data with one equivalent circuit model if we know what's happening. However, as we have seen previously, there are many steps involved for one reaction, and each reaction can typically occur either at low frequencies or mid frequencies or high frequencies. This terminology is not very, what you can say, low frequency for me can be 0.1, for what somebody else it can be 1 millihertz. So this is just a general terminology to say that at what frequencies we get different elementary processes. So now, given that if any elementary processes have relaxation times which are very similar to each other, your equivalent plots or Nyquist plot will show semicircles which will be difficult to convolute. They will be merged. And if that is the case, if you go with the preconceived notion that this is my circuit, you might make a mistake in fitting the data and you will get a wrong understanding of the processes. In order to avoid that, we need to do some of the experiments. So for example, here we see one experimental data These all are same data, but I can fit them with 4 equivalent circuits. I can fit them with having an inductor, having a Garisher with an inductor, no inductor, just Garisher, and no Garisher or inductor at all. But all of them fits. So in this case, it's very important to see what you are trying to fit. But if you're using a software such as ZView, it gives some outputs such as chi-square values, which tells you that whether the fitting is good or not. So based on that, we know that these 2 circuits are better than the other 2 circuits, but still there is a confusion. Which equivalent circuit is the correct equivalent circuit? If something like that happens, we can take in help of distribution of relaxation times. So nowadays, most of the papers have DRT techniques. So the DRT technique which I'm using is based on impedance spectroscopy genetic programming, where it also uses the universal reaction, which relates the impedance with the polarization resistance, distribution function of relaxation times, which is the y-axis here, relaxation times, which is the x-axis here, and the angular frequency. Now, your impedance plot is now converted into peaks. Now, getting the area under the peaks will give you resistances. So this impedance spectroscopy genetic programming is a free program, which I'm using from the website of Yoetzer, which is who is based in Technion, Israel Institute of Technology. So this is a very simple simulated data just to show that what is the resolution of your DRT technique. So here what I see is that if you have relaxation times of tau2, which is around 2.5 times of tau1, 3.5, I can clearly see 2 visible peaks, which is good enough. But sometimes when I have relaxation times which are similar to the tau1, visually I don't see a peak, but the numerical output of the data clearly tells there are 2 processes, and the RC numbers are very similar to the simulated data. Although it didn't show 2 peaks, but it does give an output that there are 2 processes. So this was just an example to see what is the resolution of the technique. Now, given the case before, we had 2 processes, whether I have a Garisher or I don't have a Garisher. I again simulated the data from ZView to get a Garisher element, which is shown, and get the output simulated data, which is experimental data here for the DRT. And this is the fit of the DRT. And what we see here is that 2 peaks. So Garisher element has split it into 2 responses, which corresponds to the diffusion and the capacitive components. So Garisher element is a mathematical relation, which is shown to typically fit this teardrop responses. And for our case in solid state materials, it relates solid state diffusion and the surface exchange of the gases. Now, just to refurbish, if I have this circuit, I should see 5 peaks in DRT, and if I have other circuits, I should see 4 peaks in DRT. If that is the case, I took the experimental data again, ran the DRT, and what I see is that there are 4 peaks. This indicates that there is no Garisher element. We don't need to complicate the system. Now system is very simple, just 4 processes, where the first process is again corresponding to the ohmic part, and the peak 2, peak 3, and peak 4 are responsible for the polarization resistant processes, which have a typical capacitances of 10⁻⁻⁶, -2, and -1, corresponding to the charge transfer and the mass transfer processes. So this exercise was just to see that how you can get more information from some data.
Yeah, maybe in 5 minutes, you please close.
So next is the Butler-Volmer equation. I assume everybody is doing the electrochemistry here, and everybody is aqueous electrochemist. And the electrochemistry in aqueous system is well known, well established, but the moment it comes to high temperature systems, it's not that well established. There are many reasons for it, but we are trying to relate the current voltage relationships for our systems based on positrones. So given the less time, I will just show some of the polarization resistances and the effect of bias. So here what we see is that this is a typical OCV resistance for a particular sample. even before coming here, I used to do all of my impedance at OCB, and I used to see that this is a very good material for fuel cells and electrolyzers. But I had no idea what is happening in anodic bias or cathodic bias, or what if I expose these materials to high cathodic or anodic biases. But now I'm trying to understand what happens when I apply bias. So if I apply anodic bias, what I see is that the R ohmic has decreased and the RP has also decreased. Decreasing in the RP is very obvious, but what leads to decrease in R ohmic process? The reason being, when you have applied anodic bias, that is a positive bias, you have increased the PO2, hence you have introduced some hole conduction into the system, and hence there is a short circuit, and you have not short circuit, there is some P-type or electronic conductivity in the electrolyte, and the R ohmic has decreased. Now, if I apply cathodic bias, what I see is that the resistance has increased. So what this indicates is that the material works best in anodic bias, but not so much in cathodic bias. But that might not be true, because what we are doing is we are producing water here, and there might be a competition between the aura reaction and the water adsorption. And also, water produced may inhibit the adsorption site. So if there is a competition for the active sites, the resistance has increased. So if we improve the microstructure, give more active sites, this should not be the case. And depending on the material type, this RP increase or decrease may change. So this was just a basic example to show what we can do with the biases. In summary, the 3 takeaways are: we need to understand how many protons are needed in a triple conductor. If you have introduced a material which has really high proton conductivity, but you also have an oxide conducting material which has a less hydration and still shows similar RPs, then we need to understand more about it, that how many protons are needed in a triple conductor to be a best positronic materials for fuel cells and electrolyzers for protonic cells. Next, we can model the proton conductivity, partial conductivity for all the charge carriers. And in order to design high-performing positrons, it is very important that we understand the effect of anodic and cathodic biases on electrode or polarization resistance, and then get the more information, and then we can have the relation of the current with the voltage for the high-temperature solid-state systems. So since this workshop is all about photoelectrochemical devices, this is one of the paper published from our group where they have used the double perovskites for photoelectrochemical device for efficient water splitting. So if somebody wants to see that whether the double perovskites or proton conducting ceramics can be used for the water splitting application, you can read this paper here. Next, I would like to thank the group of at UIO, the electrochemistry group. These are very happy people and they make everyone happy. And I'm very fortunate to work with Schulz and Ragnar Strandberg, who have been really good to teach me the basic of solid-state electrochemistry and also all about the proton ceramics. Next, I will leave the talk at the end on the summary slides, and I would like to thank the organizers and all of you to listening to my talk.
Well, now the talk is open. Only 1 or 2 short questions, and rest can be discussed during the lunch. You can catch here in the lunch time. Okay, I think everyone will catch you in the lunch time.
Sure.
So, absence of no questions. Let me thank her for her wonderful presentation.
Thank you.
Thank you.
Thank you. Thank you for giving your valuable insights. And also, I thank Professor Murugesh on behalf of the SWAP organization team for serving us the session chair. I would like to invite Professor Murugesh to honor Dr. Kalpana Singh with Momentum and Shot. Now it's time for lunch. I would like to request all the guests and participants move towards the botanical garden. Meal is waiting for you outside of the garden. Thank you.